Imagine the towering skyscrapers and sleek bridges of 2026. Now, what if I told you their secrets were uncovered not in a modern lab, but in dusty medieval workshops? Prepare to have your mind blown as we unveil the forgotten medieval innovations, from hidden material science to architectural marvels that are still secretly shaping the skylines you see every single day. You'll never view today's architecture the same way again. Think modern skyscrapers are built purely on 21st century genius. Think again. What if I told you the secrets to their stability, their height, even their foundational strength, were actually forged centuries ago in the dusty workshops of medieval master builders? Prepare to have your perception of construction history completely reshaped. Could a medieval mason teach a modern architect a thing or two about sustainable building or structural daring? Absolutely. We're about to expose the mind-blowing medieval innovations, from revolutionary arches to hidden material science, that are still silently shaping the skylines of February 2026. When you hear medieval, what comes to mind? Dark ages, primitive tools, backward thinking. Let me stop you right there. That perception couldn't be further from the truth, and it's time we set the record straight. The medieval period, spanning roughly from the 5th to the 15th century, was an era of extraordinary innovation in building technology. While we often credit the Industrial Revolution and modern engineering with our construction prowess, the truth is that many fundamental principles we use today were perfected by medieval craftsmen who had neither computers nor calculators, yet somehow managed to create structures so magnificent and enduring that they still dominate European skylines 8 centuries later. Consider this staggering fact. Notre Dame Cathedral in Paris stood for over 850 years before the tragic fire of 2019. The Cologne Cathedral in Germany, begun in 1248, still ranks among the tallest churches in the world. These weren't lucky accidents or divine interventions. They were the products of sophisticated engineering knowledge, advanced material science, and innovative construction techniques that would make modern engineers pause in admiration. But here's what's truly mind-blowing. Many of these medieval innovations weren't lost to history. They didn't disappear into the dusty annals of forgotten knowledge. Instead, they evolved, adapted, and integrated themselves so seamlessly into modern construction that we've forgotten their origins entirely. Today's structural engineers are using principles of load distribution perfected in 12th century France. Modern architects employ geometric design systems developed by medieval master masons. Contemporary materials scientists are rediscovering medieval mortar formulations that outperform some modern concrete. The medieval builders didn't have steel reinforcement bars or Portland cement. They couldn't run computer simulations to test their designs. They had no cranes powered by diesel engines or precision measuring instruments calibrated to fractions of millimeters. What they had was something far more valuable: centuries of accumulated practical wisdom, a deep understanding of materials and forces, and an apprenticeship system that transmitted knowledge with remarkable fidelity across generations. Think about the challenge these builders faced. They needed to construct buildings that could support massive stone vaults weighing hundreds of tons, reach heights that seemed to defy gravity, stand firm against wind, rain, earthquakes, and the test of time, create vast interior spaces without modern materials like steel or reinforced concrete. Accomplish all this using only hand tools, human and animal power, and natural materials, and they succeeded spectacularly. The medieval period saw the development of what we now call Gothic architecture, a revolutionary building style that pushed the boundaries of what was structurally possible. But Gothic architecture wasn't just about aesthetics. It was a comprehensive system of engineering solutions to complex structural problems. Every pointed arch, every flying buttress, every ribbed vault was a carefully calculated response to the fundamental challenge of building taller, lighter, and more magnificent than ever before. What's particularly fascinating is how medieval builders achieved this without the formal mathematics and physics we rely on today. They didn't calculate stress loads using equations or model structural behavior with finite element analysis. Instead, they developed practical, geometric methods that worked brilliantly. They used proportional systems, empirical testing, and a sophisticated understanding of how forces flow through a building. Modern researchers studying medieval construction techniques have been repeatedly surprised by the sophistication of these methods. When engineers analyze Gothic cathedrals using contemporary computer modeling, they often discover that medieval builders had optimized their structures with remarkable precision. The thickness of walls, the angles of buttresses, the proportions of vaults, all were carefully calibrated to balance forces and minimize material use while maximizing height and interior space. But the innovations weren't limited to grand cathedrals. Medieval builders developed construction techniques for everything from castles and bridges to mills and harbors. They invented lifting devices, scaffolding systems, and surveying instruments. They perfected mortar formulations, waterproofing methods, and foundation techniques that are still studied today. Perhaps most remarkably, they created a system of knowledge transfer, the guild system, that ensured these innovations were preserved and improved across generations. This wasn't written knowledge in textbooks. It was practical, hands-on expertise passed from master to apprentice through years of training and practice. As we journey through this exploration of medieval building technology, prepare to discover that the line between medieval and modern is far blurrier than you ever imagined. The genius of medieval builders didn't disappear when the Renaissance dawned. It became the invisible foundation upon which all subsequent architectural achievement was built. In the chapters ahead, we'll dive deep into specific innovations: the pointed arch that revolutionized load distribution, the flying buttress that made impossible heights possible, the ribbed vault that created soaring interior spaces, and many more. We'll explore medieval material science, construction equipment, planning methods, and training systems. And most importantly, we'll reveal how each of these innovations lives on in the buildings rising around us in 2026. The story of medieval building technology isn't just history, it's the secret origin story of modern construction, and it's far more fascinating than you ever imagined. The period between roughly 1100 and 1500 CE witnessed what can only be described as a construction revolution. During these 4 centuries, European builders transformed the landscape, creating structures of unprecedented height, complexity, and durability. But what triggered this revolution? And more importantly, what made it possible? The answer lies in a perfect storm of social, economic, and technological factors that came together in medieval Europe. The Catholic Church, at the height of its power and wealth, became the primary patron of monumental architecture. Competition between cities, bishops, and kingdoms drove an arms race of cathedral building, with each new structure trying to outdo the last in height, beauty, and technical achievement. But ambition alone couldn't build cathedrals. The real revolution happened in the workshops and construction sites, where practical craftsmen were systematically solving engineering problems that had stumped builders for centuries. They weren't working from theoretical principles. They were experimenting, testing, refining, and perfecting techniques through hands-on experience. Let's understand the scale of what they accomplished. The Chartres Cathedral, completed in the early 13th century, soars to a height of 113 meters, 371 feet, at its tallest point. The Beauvais Cathedral, though partially collapsed, attempted to reach even greater heights with a choir vault of 48 meters, 157 feet, a record that stood for centuries. These weren't just tall buildings. They were complex structural systems that had to be stable, functional, and constructed without any of the tools we take for granted today. The medieval construction revolution was characterized by several key developments. Before the medieval period, construction knowledge was often localized and inconsistent. The medieval era saw the rise of highly organized craft guilds, which established standards, training systems, and quality control mechanisms. Master masons became respected professionals who could command high fees and travel across Europe to share their expertise. This professionalization meant that innovations could spread more rapidly and be implemented more consistently. While medieval builders didn't have power tools, they developed increasingly sophisticated hand tools and construction equipment. The treadwheel crane, capable of lifting loads of several tons, was a medieval invention that revolutionized construction logistics. Specialized measuring instruments allowed for more precise work. Improved metalworking techniques produced better quality tools that could cut stone more accurately and efficiently. Medieval builders didn't just use materials, they studied them, tested them, and developed new formulations. Lime mortar was refined to create joints that were both strong and flexible, allowing structures to settle and shift without cracking. Stone selection became a specialized science, with builders learning to identify the best types of stone for different applications. Waterproofing techniques using lead and copper-protected buildings from the elements. Medieval master masons developed sophisticated geometric systems that allowed them to design and construct complex structures without detailed drawings or calculations. Using simple tools like compasses, squares, and marked rods, they could lay out entire buildings with remarkable precision. These geometric systems encoded proportional relationships that ensured structural stability and aesthetic harmony. The innovation of structural systems, perhaps most significantly, medieval builders developed entirely new approaches to structural engineering. The pointed arch, ribbed vault, and flying buttress weren't just aesthetic choices. They were revolutionary structural solutions that fundamentally changed what was possible in architecture. These innovations allowed builders to direct forces more efficiently, reduce the amount of material needed, and create larger interior spaces. The impact of this revolution extended far beyond Europe. As European powers expanded their influence through trade, colonization, and cultural exchange, these building techniques spread worldwide. Gothic-inspired architecture appeared in the Americas, Asia, and Africa. More importantly, the fundamental principles developed during this period became embedded in architectural education and practice globally. What makes this revolution particularly remarkable is its sustainability. Modern buildings typically have design lifespans of 50–100 years. Medieval cathedrals, built to last forever, are still standing and still functional after 800 years or more. They've survived wars, earthquakes, fires, and the simple wear of centuries. Many require remarkably little maintenance considering their age. This longevity wasn't accidental. Medieval builders understood something that modern construction has sometimes forgotten. Buildings are not just structures. They're systems that must work with natural forces, not against them. They built with materials that age gracefully, develop character over time, and can be repaired using traditional techniques. They created designs that could adapt to changing needs without requiring complete reconstruction. The medieval construction revolution also demonstrates the power of practical, empirical knowledge. These builders didn't wait for formal scientific theory to catch up with their needs. They experimented, failed sometimes. Yes, some medieval buildings did collapse, learned from those failures, and refined their techniques. This iterative, experiential approach to problem-solving produced solutions that were often more elegant and effective than theoretically optimal designs. As we examine specific innovations in the chapters ahead, keep in mind that each one emerged from this broader context of systematic innovation and practical problem-solving. The pointed arch wasn't invented by a lone genius having a eureka moment. It evolved through countless iterations as builders sought better ways to span openings and support loads. The flying buttress developed because builders needed to counteract lateral forces while maintaining large window openings. Every innovation we'll explore was part of an interconnected system of advancing knowledge and capability. The medieval construction revolution teaches us several important lessons that remain relevant in 2026. First, technological progress doesn't always require new materials or tools. Sometimes the greatest innovations come from using existing resources more intelligently. Second, practical experience and hands-on experimentation can produce solutions that pure theory might miss. The medieval builder's empirical approach led to discoveries that formal engineering science only later explained. Third, knowledge transfer systems matter. The medieval guild system, despite its limitations, successfully transmitted complex technical knowledge across centuries. Modern construction could learn from this emphasis on mentorship and hands-on training. Fourth, building for longevity and sustainability isn't a new concern. It's an ancient wisdom that we've sometimes forgotten in our rush for quick, cheap construction. Finally, the revolution reminds us that construction is fundamentally a human endeavor. The magnificent buildings of the medieval period weren't created by machines or algorithms. They were crafted by skilled hands and thoughtful minds working together over decades and sometimes centuries. As we proceed to explore specific innovations, remember that each one represents not just a technical achievement, but a triumph of human creativity, persistence, and collaborative effort. The medieval construction revolution wasn't just about building bigger and taller. It was about fundamentally reimagining what was possible and then developing the techniques to make those visions real. Let's start with perhaps the most recognizable and revolutionary innovation of medieval architecture, the pointed arch. If you've ever looked at a Gothic cathedral and thought, that's pretty, but is it really that special? Prepare to have your mind changed. The pointed arch wasn't just an aesthetic choice. It was a game-changing structural solution that made everything else possible. Now, let us discuss the problem with round arches. To understand the brilliance of the pointed arch, we need to understand the limitations it overcame. Roman and Romanesque builders had used round, semicircular arches for centuries. These were structural marvels in their own right. They allowed builders to span openings without using a solid lintel, and they distributed weight effectively. But round arches had serious limitations. First, their height was fixed by their span. If you wanted an arch 10 meters wide, it would be 5 meters high, period. This meant that to create arches of different widths that reached the same height, essential for creating regular vaulting patterns, you need complex and often structurally compromised solutions. Second, round arches generated significant lateral thrust, outward force pushing on the walls. As architects built taller and wanted larger openings, these lateral forces became increasingly problematic. Thick, massive walls were needed to resist them, which limited height and interior space. Third, round arches were relatively inflexible. Once you decided on a span, everything else was determined. This made it difficult to adapt designs or correct problems during construction. Enter the pointed arch, which appeared in European architecture in the late 11th century, though it had been used earlier in Islamic architecture. At first glance, it might seem like a simple shape change, but the engineering implications were profound. A pointed arch is formed by two arc segments meeting at an apex. Unlike a round arch, where the geometry is fixed, a pointed arch can have different proportions while spanning the same opening. A shallow pointed arch might have arcs from large circles. A steeply pointed arch uses arcs from smaller circles. This flexibility was revolutionary. Here's why pointed arches changed everything. 1. Vertical force direction. The most crucial advantage is how pointed arches redirect forces. While round arches push significantly outward, pointed arches direct more force vertically downward. Think of it this way. The steeper the sides of the arch, the more the weight wants to travel straight down rather than spreading outward. This means less lateral thrust on walls. When engineers analyze this using modern structural analysis, they find that a pointed arch can reduce horizontal forces by 30–50% compared to a round arch of the same span. That's enormous. It means you can build with thinner walls, larger openings, or reach greater heights, or all three at once. 2. Height flexibility. Because the proportions of a pointed arch can vary, builders could make arches of different widths reach the same height. Imagine you're vaulting a cathedral. You need arches across the nave wide, across each aisle narrower, and diagonally across each bay widest. With round arches, these three spans would produce three different heights, creating a structural nightmare. With pointed arches, you simply adjust the angle of the point. Need more height from a narrower span? Use a steeper point. Need to keep a wide span from getting too tall? use a shallower point. This flexibility allowed for much more sophisticated vaulting systems and more regular, stable structures. 3. Adaptability during construction. Medieval construction took decades or even centuries. Pointed arches gave builders more flexibility to adjust designs as they went. If foundation settling caused problems, or if resources changed, or if a new master mason arrived with different ideas, pointed arches could be adapted more easily than rigid round arches. This adaptability was crucial for the long-term projects typical of medieval cathedral building. A structure that couldn't accommodate change wouldn't survive generations of construction. 4. Reduced material requirements. With less lateral thrust, you need less material to resist those forces. Medieval builders, acutely aware of the cost and effort of quarrying, transporting, and carving stone, recognized that pointed arches allowed them to build lighter and more economically. The material savings weren't trivial. We're talking about potentially thousands of tons of stone for a major cathedral. The mathematics behind the magic now, medieval builders didn't have modern structural analysis software, but they understood these principles intuitively through experience and practical geometry. Modern engineers studying medieval structures have been amazed to discover how precisely forces were balanced. When you analyze a pointed arch using contemporary methods, you find that the forces flow along the curve of the arch in compression, pushing forces, which stone handles beautifully. There's minimal tension, pulling forces, which is critical because stone is weak in tension and strong in compression. The pointed geometry optimizes this compression path better than a round arch, especially for tall, narrow openings. The angle at the apex matters tremendously. An equilateral pointed arch, where the two arcs come from circles whose centers are at the opposite base of the arch, provides an excellent balance of height and lateral force reduction. This proportion appears repeatedly in Gothic architecture, suggesting medieval builders recognized its structural advantages. Lancet arches, which are tall and narrow with very steep sides, push even more force vertically and create dramatic interior spaces. They reduce lateral thrust even further, but require careful balancing with other structural elements. Drop arches, which are shallower, were sometimes used where height was limited, but span needed to be maintained. You might think pointed arches are ancient history, relevant only to neo-Gothic revivals and tourist cathedrals. Think again. The structural principles embodied in pointed arches remain relevant to modern construction, though often in disguised forms. Contemporary long-span structures like sports arenas and exhibition halls use curved structural members that operate on similar principles, redirecting loads to optimize force paths, allowing for large interior spaces without massive support structures. While we now build with steel and reinforced concrete rather than stone, the fundamental insight remains. The shape of an arch or structural curve profoundly affects how it handles loads. Modern bridge design frequently employs pointed arch principles. Many elegant pedestrian bridges use pointed arch shapes specifically to minimize lateral forces on abutments while creating aesthetically pleasing forms. The mathematical optimization that goes into these designs often arrives at geometries remarkably similar to medieval pointed arches. Even in skyscraper design, the concept of directing loads efficiently, inherited directly from medieval arch technology, remains fundamental. Modern tall buildings use core and outrigger systems, tube structures, and other innovations to direct wind loads and gravity loads efficiently down to foundations. This is conceptually similar to how pointed arches directed forces down columns and buttresses to foundations. The pointed arch also influenced the development of Gothic revival architecture in the 19th century, which produced thousands of churches, civic buildings, and universities across Europe and North America. Many of these structures remain in use today, their pointed arches not just decorative elements, but functional structural members. Walk through any major city in 2026 and you'll see the legacy of the pointed arch. Sometimes it's obvious, a Gothic revival church or courthouse, its pointed windows and doorways clearly echoing medieval forms. Sometimes it's subtle, a modern building whose structural elements reveal, under analysis, geometric principles first perfected in medieval France. But the true legacy isn't just in the forms we see. It's in the fundamental understanding that geometry matters structurally, that form and function can and should work together, and that elegant solutions often come from deeply understanding how forces flow through structures. The pointed arch teaches us that innovation doesn't always mean new materials or technologies. Sometimes the greatest breakthroughs come from rethinking how we use what we already have. Medieval builders couldn't invent new materials or discover new physical principles, but they could, and did, develop new geometric forms that used existing materials far more effectively. When modern structural engineers optimize a design, they're participating in a tradition that stretches back to those medieval master masons who first realized that changing the shape of an arch from round to pointed could transform what was architecturally possible. They were doing structural optimization long before computers existed, using geometry, experience, and careful observation instead of finite element analysis. The pointed arch represents one of humanity's great insights, that the solution to building taller, spanning further, and creating more magnificent interior spaces didn't require waiting for new technologies to be invented. It required only looking at a familiar element, the arch, with fresh eyes and asking, what if we changed this? That question, and the centuries of refinement that followed, gave us structures that still inspire 800 years later. It gave us engineering principles that remain valid in an age of steel and computer-aided design. And it reminds us that sometimes the most transformative innovations come not from adding more, but from understanding better. The pointed arch, simple in concept, revolutionary in impact, and still shaping how we build in 2026. Not bad for a medieval innovation that required no new materials, no machines, and no mathematical formulas, just careful observation, practical experimentation, and brilliant insight into the nature of structural forces. If the pointed arch revolutionized how forces moved through an arch, the flying buttress revolutionized how forces moved through an entire building. This innovation, arguably the most visually distinctive feature of Gothic architecture, represents one of the most elegant structural solutions ever devised, and its principles continue to influence modern engineering in ways that might surprise you. Imagine you're a medieval master mason with an ambitious vision. You want to build a cathedral with walls that soar 40 meters high, pierced by enormous windows that flood the interior with light. Your pointed arches and ribbed vaults, which we'll discuss shortly, are directing loads efficiently downward, but there's still substantial lateral thrust forces pushing outward on the upper walls, threatening to topple them outward. The old solution was simple. Make walls thick enough to resist these forces through sheer mass. But thick walls are expensive, require enormous amounts of material, block light, and ultimately limit how tall you can build. There had to be a better way. What if, instead of making the whole wall thick, you could add support exactly where it's needed? What if you could counteract the outward thrust at its source, high up on the wall where the vault meets it, while leaving the wall itself thin and perforated with windows? This insight led to one of the most ingenious structural innovations in history, the flying buttress. A flying buttress is an arched structure that spans from an exterior pier, a separate vertical support standing away from the building, to the upper portion of a wall, right where lateral thrust is generated. It's called flying because it literally flies through the air, creating a half-arch that bridges from the external support to the building wall. Here's the brilliant part. The flying buttress catches the lateral thrust exactly where it's generated, at the top of the wall where the vault pushes outward, and redirects it down and out to the massive external pier. The pier, in turn, directs these forces down to the ground through its own weight and mass. Think of it like this. Instead of the thin upper wall having to resist huge lateral forces by itself, it has a helper. The flying buttress acts like a giant hand pushing back against the wall, keeping it vertical. The external pier is the solid foundation that hand is pushing from. This system allowed medieval builders to achieve something unprecedented: walls that were structurally thin curtains of stone and glass, supported by external skeletal frameworks. The wall itself became almost incidental to the structure. It was the system of piers, flying buttresses, and internal vaults that carried the real loads. The engineering principles, modern structural analysis, reveals just how sophisticated flying buttress systems really are. When engineers model these structures, they find several key design features that demonstrate deep understanding of force flow. 1. Angle and positioning. The angle of a flying buttress is crucial. Too steep, and it doesn't effectively counteract horizontal thrust. Too shallow, and it creates its own excessive horizontal forces at the pier. Medieval builders found that an angle around 45 degrees, though this varied, worked optimally for most situations. The height at which the buttress meets the wall is also critical. It must connect right where the vault generates thrust. Study any Gothic cathedral, and you'll see that flying buttresses don't attach randomly. They align precisely with the points of greatest lateral force. 2. The chain of forces. Flying buttresses work as part of a complete structural system. The vault pushes on the wall is supported by the flying buttress. The buttress directs forces to the external pier, and the pier directs everything to the ground. It's a beautiful chain of compression forces, with each element playing its specific role. Medieval builders often used multiple tiers of flying buttresses at different heights, each counteracting thrust at a different level. This created redundancy. If one element underperformed, others could compensate. It's the same principle used in modern redundant structural systems. 3. The use of weight. Those external piers aren't just solid blocks. They're often topped with decorative pinnacles. But these pinnacles aren't merely decorative. They're weights that help stabilize the pier. By adding vertical load directly over the pier, they increase its resistance to being pushed outward by the flying buttress. It's counterintuitive until you understand the physics. Adding weight makes the system more stable, not less. This demonstrates sophisticated understanding of how vertical loads can stabilize structures against lateral forces, a principle used extensively in modern engineering, from foundation design to skyscraper stability systems. 4. Material efficiency. The genius of flying buttresses is that they place material only where it's structurally necessary. Instead of a massive thick wall, you have a thin wall, much less material, plus relatively slender buttressing elements. The total material volume is often less than a traditional thick wall design, yet the structure is stronger and can be taller. This represents early structural optimization, achieving maximum strength and stability with minimum material. It's exactly what modern engineers do with computer-aided optimization, but medieval builders did it through geometric reasoning and practical experience. Historical development and variation. Flying buttresses didn't appear fully formed. They evolved over decades of experimentation. Early Gothic structures like the Cathedral of Sens, begun 1135, used relatively simple, hidden buttressing. As builders gained confidence, buttresses became more elaborate and were moved outside the building entirely, where they became defining visual features. Different regions developed distinctive buttress styles. French cathedrals often feature elegant, single-arch buttresses. English Gothic developed perpendicular buttresses with more vertical emphasis. Spanish and German Gothic sometimes used double or triple tiers of buttresses for especially tall structures. The Beauvais Cathedral represents perhaps the most ambitious use of flying buttresses ever attempted. Its builders pushed the limits of what was possible, creating a structure so tall and daring that it partially collapsed and had to be rebuilt with additional support. This failure taught valuable lessons about the limits of the system, lessons that informed subsequent cathedral construction throughout Europe. You might assume flying buttresses are purely historical artifacts, relevant only to medieval architecture and its neo-Gothic revivals. But the structural principles they embody remain highly relevant to modern engineering. Lateral support systems in modern buildings. Contemporary tall buildings face tremendous lateral forces from wind. While we don't use flying buttresses per se, we use external support systems that operate on similar principles. Outrigger systems in skyscrapers. which connect the central core to exterior columns, work conceptually like flying buttresses. They resist lateral forces by engaging exterior supports. The famous tensile cables on some modern cable-stayed structures serve a similar function to flying buttresses. They provide external support that allows for thin, light primary structures. The principles of external support, load redistribution, and structural efficiency pioneered in medieval flying buttresses live on in these modern systems. Bridge design. Many modern arch bridges use external tie rods or cables that function similarly to flying buttresses. They counteract lateral thrust by providing external support. Some pedestrian bridges explicitly use buttress-like elements to create dramatic cantilevers and spans. Earthquake engineering. Modern seismic retrofitting sometimes uses external buttressing to strengthen existing structures. Steel or concrete elements are added externally to resist lateral forces from earthquakes. It's the same basic principle medieval builders used, adapted for modern materials and challenges. Space frame and digrid structures. Some contemporary buildings use exposed external structural frameworks, diagrid, diagonal grid systems, where the structure is visible on the exterior. While the specific forms differ, the concept of moving structure to the exterior to free up interior space and optimize load paths comes directly from Gothic precedents like flying buttresses. The CCTV headquarters in Beijing, with its dramatic external structural loop, represents a modern exploration of similar ideas structure as external framework, creating interior freedom and dramatic exterior form. Sustainable design. Flying buttresses also teach lessons about sustainable, material-efficient design. By placing structure only where needed, medieval builders achieved remarkable efficiency. Modern sustainable architecture increasingly embraces this approach, optimizing structures to minimize material use while maintaining strength and stability. A testament to empirical engineering, perhaps what's most impressive about flying buttresses is that they were developed entirely through empirical observation and practical testing. Medieval builders had no equations for calculating lateral thrust, no computer models to simulate behavior, no materials testing laboratories. They had geometry, practical experience, and careful observation of what worked and what didn't. When a structure cracked or failed, as happened occasionally, they studied the failure, understood what went wrong, and refined their approach. This iterative, evidence-based method produced solutions that still impress structural engineers today. Modern analysis of Gothic cathedrals consistently reveals that medieval builders got it right. The proportions of buttresses, their angles, their positioning, all optimized through experience rather than calculation, turn out to be remarkably close to what modern engineering would specify for similar conditions. The visual impact. We can't discuss flying buttresses without acknowledging their visual drama. They transform buildings into dynamic sculptural compositions, creating rhythms of light and shadow, void and solid. They make structure itself beautiful, visible, comprehensible, and inspiring. This aesthetic dimension matters because it demonstrates that structure doesn't have to be hidden. Some of the most beautiful architecture in history celebrates structure, makes it visible, and uses it as a primary source of aesthetic expression. Flying buttresses taught architects that structural honesty could be beautiful. Modern architecture has sometimes forgotten this lesson, hiding structure behind facades and treating it as a necessary evil rather than a source of beauty. But the best contemporary architecture, structures by engineers like Santiago Calatrava or architects like Norman Foster, returns to this Gothic principle: structure as sculpture, engineering as art. Legacy and lessons. The flying buttress represents several key lessons that remain relevant in 2026. First, external support systems can be more efficient than internal ones. Don't be constrained by thinking structure must be contained within the building envelope. Second, material efficiency and structural elegance often go hand in hand. The most beautiful solutions are often also the most efficient. Third, making structure visible can enhance rather than detract from architecture. Celebrating how buildings stand up connects people to fundamental forces and makes spaces more comprehensible. Fourth, structural innovation doesn't require new materials. It requires new thinking about how to use existing materials. Finally, empirical, iterative development can produce solutions as good as or better than purely theoretical approaches. Sometimes you have to build it, test it, and refine it to get it right. The flying buttress, a daring structural innovation, a triumph of empirical engineering, and a beautiful demonstration that sometimes the best way to support something is to reach out and give it a hand, even if that hand flies through space on an elegant stone arch. 800 years later, we're still learning from this medieval marvel. If pointed arches and flying buttresses revolutionized walls and support, ribbed vaults revolutionized what happened overhead. The ribbed vault represents one of the most sophisticated structural innovations of the medieval period, a system that turns ceilings from heavy, passive elements into active participants in a building's structural system, and its influence on modern construction, more profound than you might imagine. The weight problem. To understand the brilliance of ribbed vaults, we need to understand the challenge medieval builders faced with roofs and ceilings. Stone vaulting, using stone to create arched ceilings, had been practiced since Roman times. But traditional barrel vaults, continuous arch shapes running the length of a space, and groin vaults, where two barrel vaults intersect at right angles, had serious limitations. These traditional vaults were incredibly heavy. We're talking about solid stone structures, perhaps a meter thick, spanning large spaces. The weight was crushing, literally. Every square meter of vault weighed several tons, and all that weight pushed outward on the walls supporting it, requiring massive supports. Moreover, these vaults were difficult to construct. They required continuous formwork, temporary wooden framework, to support them during construction. This formwork had to hold the entire weight of the vault until the keystone was placed, and the structure became self-supporting. For large vaults, this meant enormous amounts of timber and complex scaffolding. The construction process was also risky and inflexible. Once you started building a vault, you were committed to the design. Making changes mid-construction was nearly impossible. And if something went wrong, if the formwork settled unevenly or the mortar didn't cure properly, the entire vault could collapse. Medieval builders needed a better system, one that was lighter, easier to construct, and more adaptable. The ribbed revolution, the ribbed vault was the answer. Instead of a solid, continuous surface of stone, ribbed vaults use a framework of stone ribs, essentially stone arches, with thinner infill panels between them. Imagine a ceiling where the major structural forces are carried by visible stone ribs, like the framework of an umbrella, with lighter stone panels filling the spaces between. This might sound like a simple modification, but it transformed everything about how vaults were built and how they performed structurally. The structural advantages. 1. Reduced weight. The most obvious benefit is reduced weight. By using stone only where it's structurally necessary, the ribs, and filling the spaces between with thinner panels, you dramatically reduce the total weight of the ceiling. Some ribbed vaults weigh 30–40% less than comparable solid vaults covering the same space. Less weight means less lateral thrust on walls, which means thinner walls, taller buildings, and larger openings for windows. It's a cascading series of benefits, all flowing from this single innovation. 2. Directed load paths. Ribbed vaults are beautiful demonstrations of structural efficiency. The ribs act as arches, carrying loads in compression down to supporting columns or walls. The forces flow along these visible stone ribs in clearly defined paths, rather than spreading throughout a continuous vault surface. This directed load path means you can provide support exactly where it's needed, at the points where ribs meet walls or columns. Between these points, walls can be thinner or pierced with windows. The famous Gothic walls of glass were possible only because ribbed vaults concentrated loads at specific points, rather than distributing them along entire wall lengths. Modern structural analysis confirms what medieval builders understood intuitively. The ribs do nearly all the structural work. The infill panels carry their own weight and help stabilize the ribs, but the major forces flow through the ribs themselves. 3. Easier construction. The construction advantages were enormous. Instead of building formwork to support the entire vault surface, builders only needed formwork for the ribs. Once the ribs were complete, they provided a permanent framework that supported the lighter infill panels. This meant less timber required, faster construction, and more flexibility. You could build the ribs of one vault while simultaneously working on infill panels in another. The construction process became more modular and efficient. The ribs also acted as permanent construction aids. Workers could move across them while building the infill, and they provided reference points for ensuring proper vault geometry. 4. Greater span and height. With reduced weight and more efficient load paths, ribbed vaults could span larger distances and reach greater heights than solid vaults. The dramatic vertical interior spaces of Gothic cathedrals, often over 40 meters from floor to vault, were possible only because ribbed vaults made such heights structurally feasible. The evolution of complexity, like other Gothic innovations, ribbed vaults evolved from simple to increasingly complex over time. Early Gothic vaults used relatively simple rib patterns, typically 4 ribs meeting at a central point, dividing each vault bay into 4 segments. As builders gained experience and confidence, rib patterns became more elaborate. Tierceren ribs, additional ribs connecting to intermediate points, created more complex geometries. Lierne ribs, short ribs connecting other ribs rather than extending to walls, created intricate patterns. Eventually, this led to fan vaults, spectacular late Gothic vaults where ribs radiate outward like fans, creating an effect like stone lacework overhead. Some late medieval vaults featured dozens of ribs creating intricate patterns. These weren't just decorative. Each rib played a structural role, distributing forces and stiffening the overall system. The famous vault of King's College Chapel in Cambridge, with its elaborate fan vaulting, is both a structural system and a work of art. The geometry of vaulting. One of the most fascinating aspects of ribbed vaulting is how medieval builders used geometry to solve structural problems. They didn't have the mathematics to calculate precisely how forces flowed through three-dimensional rib systems. Instead, they used proportional systems based on squares, triangles, and circles. The plan of a typical Gothic vault bay is often based on a square. Diagonal ribs cross this square. Transverse ribs span its width. Longitudinal ribs run its length. Additional ribs might be positioned using geometric subdivisions. Divide the square into thirds, or inscribe circles within it, or use other geometric constructions. What's remarkable is that these geometric systems, developed through practical experience and aesthetic intuition, produced structurally efficient results. Modern engineers, analyzing these vaults, find that the proportions and rib positions often closely approximate what structural optimization would recommend. It's another example of empirical knowledge matching theoretical analysis, practical builders solving problems through experience and geometric reasoning, arriving at solutions that formal engineering science later validated. Modern applications. The principles embodied in ribbed vaults appear throughout modern construction, though often in disguised forms. 1. Space frame structures. Modern space frames, three-dimensional structural frameworks used for roofing large spans like airports, sports arenas, and exhibition halls, are direct descendants of ribbed vault thinking. Like ribbed vaults, space frames use a framework of structural members, typically steel or aluminium, with infill panels, glass, metal, or other materials between them. The principle is identical. Carry major loads through a framework, use lighter material for infill, create efficient load paths, and achieve structural economy through geometric organization. Space frames are essentially ribbed vaults translated into modern materials and mathematics. 2. Concrete shell structures. Mid-20th century engineers like Pier Luigi Nervi created stunning reinforced concrete structures that echo ribbed vault principles. Nervi's Palazzetti dello Sport and exhibition halls use concrete ribs with thinner concrete panels between them, ribbed vaults in concrete rather than stone. These structures demonstrated that the medieval insight about frameworks versus continuous surfaces remained valid even with modern materials and construction methods. 3. Grid shells. Modern grid shell structures, curved frameworks of wood, steel, or other materials creating dome-like or vaulted forms, apply ribbed vault principles. The British Museum's Great Court roof is an excellent example, a lattice of steel members with glass panels between them, creating a dramatic curved ceiling over the museum's courtyard. 4. Longspan roof systems. Contemporary longspan roofs for buildings like convention centers and sports stadiums use structural systems remarkably similar to ribbed vaults in principle. Major beams or trusses carry primary loads. Lighter decking spans between them. The specific forms differ, but the structural logic framework plus infill comes straight from medieval vaulting. 5. Sustainable prefabricated systems. Some contemporary sustainable building systems use prefabricated rib-like frameworks with infill panels. These systems echo ribbed vault thinking. Factory build the primary structure, fill in between structural members with lighter materials, create efficient assembly processes. Material efficiency and sustainability. From a sustainability perspective, ribbed vaults teach important lessons. They demonstrate how to achieve required strength with minimum material. Use material only where it's structurally necessary, not uniformly throughout. This principle of material efficiency is increasingly crucial as we face resource constraints and environmental impacts of construction. The medieval builder's insight that you don't need solid mass everywhere. That strategic placement of material in efficient geometries can outperform brute force approaches is exactly what sustainable design requires. Modern optimization algorithms, when tasked with minimizing material use while maintaining strength, often produce solutions resembling ribbed frameworks with infill, arriving mathematically at conclusions medieval builders reached empirically. The aesthetic dimension. We can't discuss ribbed vaults without acknowledging their visual impact. Looking up at a Gothic vault is a transcendent experience. The ribs draw your eye upward, creating a sense of soaring height and lightness despite the massive stone construction. The visible structure becomes beautiful. The ribs aren't hidden behind decorative elements, they are the decoration. This structural honesty creates spaces where people intuitively understand how the building works. They can see the framework, trace the loads, comprehend the structural system. This is architectural education at its best, buildings that teach people about structure simply by being visibly and honestly structured. It's a lesson modern architecture sometimes forgets, but the best contemporary design remembers. The knowledge transfer. The construction of ribbed vaults represented one of the most complex technical challenges medieval builders faced, ensuring that multiple curved ribs met precisely at keystones, maintaining proper geometry throughout, and coordinating the complex construction sequence required enormous skill. This skill was transmitted through the apprenticeship system we'll discuss later. Master masons developed detailed knowledge of vault geometry, construction sequences, and problem-solving strategies. They passed this knowledge to apprentices through years of hands-on training. The fact that this knowledge successfully transferred across generations, that we see similar vaulting techniques used across centuries and continents, testifies to the effectiveness of this training system. It's a model for preserving and transmitting complex technical knowledge that remains relevant. Legacy and impact. The ribbed vault's influence extends far beyond its immediate structural benefits. It demonstrated that heavy, passive elements, like solid vaults, could be reimagined as active structural systems, like ribbed frameworks. It showed that complex three-dimensional geometries could be planned and constructed using practical geometric methods rather than advanced mathematics. It proved that reducing weight and material could increase rather than decrease structural capabilities. It established principles of framework plus infill that remain fundamental to modern construction. Most importantly, it taught architects and engineers that ceiling and roof systems aren't just coverings. They're integral parts of structural systems that, when properly designed, can enhance the entire building's performance. The ribbed vault represents medieval structural thinking at its finest, identifying a problem. Heavy, difficult to build solid vaults, understanding the fundamental structural requirements, carry loads in compression along efficient paths, and developing an elegant solution that addressed multiple challenges simultaneously. When you see exposed structural systems in modern buildings, visible steel trusses, concrete ribs, space frame roofs, you're seeing descendants of ribbed vault thinking. When architects celebrate structure rather than hide it, they're honoring a tradition established in medieval cathedral workshops. The ribbed vault, lighter than solid stone, stronger than appearances suggest, and teaching lessons about structural efficiency that remain valid 8 centuries later. Not bad for an innovation developed entirely through practical experimentation and geometric reasoning. In 2026, as we design structures with advanced materials and powerful computers, we're still applying principles that medieval master masons discovered while building their magnificent vaulted ceilings. The specifics have changed, but the fundamental insights remain eternal. When we think of medieval construction breakthroughs, our minds immediately go to the dramatic forms, the soaring arches, the flying buttresses, the intricate vaults. But some of the most revolutionary innovations happened at a much smaller scale, in the very material that held everything together: mortar. Modern scientists studying medieval structures have made a startling discovery. Many medieval mortars actually improve with age. They develop properties over centuries that make them stronger, more flexible, and more durable than when they were first applied. Some can even self-heal, automatically sealing small cracks without human intervention. This isn't mystical or supernatural. It's advanced material science that we're only now beginning to fully understand and replicate. To understand medieval mortar innovations, we need to briefly revisit Roman concrete. The Romans created structures of remarkable durability using a mixture of lime, volcanic ash, pozzolana, and aggregate. The Pantheon in Rome, with its massive unreinforced concrete dome, has stood for nearly 2,000 years. Roman harbor structures have survived underwater for millennia, but after the fall of the Western Roman Empire, much of this knowledge was lost or fragmented. Medieval builders had to rediscover and reinvent these technologies, often arriving at different and sometimes superior solutions. Medieval builders primarily used lime mortar, a mixture of slaked lime, calcium hydroxide, sand, and water. This might sound simple, even primitive compared to modern Portland cement, but the reality is far more sophisticated. The production of lime mortar began with burning limestone, calcium carbonate, in kilns at temperatures around 900 degrees C. This drove off carbon dioxide, leaving quicklime, calcium oxide. The quicklime was then carefully slaked by adding water, creating slaked lime, calcium hydroxide, in a highly controlled process that generated tremendous heat. This slaked lime was then mixed with carefully selected sand and water to create mortar. But here's where medieval expertise came into play. The proportions, mixing methods, curing procedures, and even seasonal timing of mortar production all dramatically affected the final properties. When lime mortar is applied, something remarkable happens over the following months and years. It slowly absorbs carbon dioxide from the air, gradually converting back to limestone. This process, called carbonation, is essentially the reverse of the original limestone burning. But this isn't just a chemical curiosity. It's the key to lime mortar's extraordinary properties. As carbonation proceeds, the mortar gradually becomes harder and stronger. Unlike modern cement, which achieves most of its strength in days or weeks, lime mortar continues strengthening for decades or even centuries. Medieval builders understood this empirically, even without modern chemical theory. They knew that lime mortar needed time to mature, that it performed differently in different conditions, and that structures improved with age if properly built. Here's where it gets really interesting. Modern researchers have discovered that lime mortar can automatically seal hairline cracks through a process called autogenous healing. Here's how it works. When a small crack forms in lime mortar, it exposes fresh calcium hydroxide to air and moisture. This exposed material begins carbonating, forming new calcium carbonate crystals. These crystals gradually fill the crack, sealing it. The process requires only air, moisture, and time, no human intervention. This self-healing property means that lime mortar structures can tolerate small movements and settlements without accumulating damage. Tiny cracks that would propagate and worsen in modern cement mortar can actually seal themselves in lime mortar. This isn't just theory. Researchers have documented this process in laboratory tests and observed it in historical structures. It's one reason medieval buildings have survived so well. They were built with materials that could repair themselves. Another crucial property of lime mortar is its flexibility. Unlike rigid modern cement, lime mortar has slight elasticity. It can accommodate small movements without cracking. This is essential in large masonry structures, which inevitably settle and shift slightly over time. Medieval buildings, constructed entirely of relatively soft materials, stone and lime mortar, could flex and adjust as foundations settled or ground moved. The entire structure acted as a coherent system, distributing stresses rather than concentrating them. Modern cement, while stronger in pure compression, is brittle. It cracks rather than flexing. When modern cement is used to repair historic lime mortar buildings, it often causes problems because it's incompatible, too rigid, too impermeable, creating stress concentrations and preventing the natural movement that lime mortar accommodates. Lime mortar is porous and breathable. It allows water vapor to pass through. This might seem like a weakness, but it's actually crucial for building health, especially in the damp European climate where most medieval construction occurred. Water inevitably enters masonry walls through rain, condensation, and ground moisture. In a lime mortar building, this moisture can slowly evaporate through the mortar joints, preventing accumulation that would cause decay, freeze damage, or salt crystallization. Modern cement, being much less permeable, can trap moisture in walls. This is why cement repointing of old lime mortar buildings often leads to accelerated stone decay. Moisture can't escape through the cement joints, so it exits through the softer stone, bringing dissolved salts that crystallize and cause spalling, surface breakdown. Medieval builders didn't understand vapor permeability in modern scientific terms, but they observed its effects and worked with it rather than against it. Regional variations and innovations. Medieval mortar wasn't uniform across Europe. Different regions developed distinctive formulations based on available materials and local conditions. Hot lime mixing. Some medieval builders used hot lime mixing, adding quicklime directly to the mortar mix rather than fully slaking it first. This created a mortar that generated heat during initial curing and achieved faster early strength. Evidence of this technique has been found in various medieval structures, and recent scientific analysis suggests it may have contributed to exceptional durability in some cases. Additives and pozzolans. Medieval builders experimented with various additives to enhance mortar properties. In regions with volcanic materials, they used volcanic ash, following Roman precedent, to create hydraulic mortars that could set underwater or in damp conditions. In regions without volcanic materials, builders discovered that crushed brick, tile, or pottery could serve similar functions. These fired clay materials contained reactive silicates that reacted with lime to create hydraulic properties. This innovation, using crushed ceramics as artificial pozzolans, was a significant medieval advancement. Other additives included animal blood, which acted as an air entraining agent, creating tiny bubbles that improved freeze-thaw resistance, milk, cheese, or other dairy products, providing proteins that enhanced bonding, beer or other fermented beverages, contributing sugars that modified setting characteristics, eggs, particularly egg whites, used in fine plasterwork, natural fibers, straw, hemp, animal hair. For reinforcement and crack resistance, these might sound like folk remedies or superstitious practices, but modern analysis reveals that many had genuine technical benefits. Medieval builders were conducting materials science experiments, using the materials available to them. The seasonal calendar. Medieval builders followed seasonal calendars for mortar work, understood through centuries of experience. Mortar wasn't produced year-round, certain times were better for different aspects of the process. Lime burning often occurred in late summer or early fall when wood fuel was driest. Slaking might wait for cooler weather. Actual construction with mortar was typically avoided in winter, when freezing could disrupt curing, and sometimes limited in the hottest summer months. This seasonal rhythm wasn't arbitrary tradition. It was practical optimization of material performance based on environmental conditions. Modern research confirms that lime mortar cured at moderate temperatures and humidity levels often performs better than mortar subjected to temperature extremes during curing. Modern rediscovery. In the 20th century, Portland cement largely replaced lime mortar in construction. Cement had advantages: faster strength gain, higher ultimate strength, more consistent performance, easier quality control. For many applications, it was genuinely superior. But by the late 20th century, problems became apparent. Historic buildings repointed with cement were deteriorating faster than before. Modern cement structures were showing durability issues, cracking, spalling, reinforcement corrosion that centuries-old lime mortar structures had avoided. This prompted renewed interest in lime mortar technology. Researchers began studying why medieval mortars performed so well and how to replicate their properties. The results have been enlightening. We now understand that lime mortars' apparent weaknesses, slower strength gain, lower ultimate strength, porosity, are actually sophisticated adaptations that provide long-term benefits: self-healing, flexibility, breathability, and compatibility with stone. Contemporary applications. Today, lime mortar is experiencing a renaissance in several contexts. Historic preservation. Conservation professionals now insist on lime mortar for repairing historic structures. Using compatible materials preserves the building's ability to function as their builders intended. Sustainable construction. Lime mortar has environmental advantages over cement. Its production requires lower temperatures, lower energy, and it reabsorbs carbon dioxide throughout its life, partially offsetting production emissions. Some calculations suggest lime mortar can be carbon neutral or even carbon negative over its lifetime. Innovative modern materials. Researchers are developing new materials inspired by lime mortar principles. Self-healing concretes that use bacteria, encapsulated healing agents, or other mechanisms to automatically repair cracks are direct descendants of medieval self-healing lime mortar research. Some ultra-high-performance concretes incorporate principles learned from studying historical mortars, optimizing particle sizes, using pozzolanic materials, controlling carbonation to enhance rather than damage the material. Natural building movement. Natural building advocates are returning to lime mortars and related materials, recognizing their health benefits: breathability, lack of toxic components, environmental advantages, and aesthetic qualities. The science we're still discovering. Modern analysis continues revealing sophisticated aspects of medieval mortar that weren't previously understood. Electron microscopy reveals that lime mortar has a complex nanoscale structure with properties that emerge from this fine-scale organization. The interface between lime binder and sand particles is particularly complex, with gradations and interactions that contribute to overall performance. Recent research suggests that microorganisms living in lime mortar may contribute to its properties, potentially accelerating carbonation or producing biominerals that enhance strength. This opens fascinating questions about whether medieval mortars harbored beneficial microbial communities. The calcium carbonate crystals that form during carbonation don't arrange randomly. They develop preferred orientations and interlocking structures that optimize strength. Medieval mortars show particularly well-organized crystal structures, suggesting production and curing methods that promoted optimal crystal formation. The more we study medieval mortars, the clearer it becomes that builders were conducting sophisticated materials engineering. Variations in composition weren't random or haphazard. They were intentional responses to specific structural requirements. Load-bearing mortars in critical areas often have different compositions than mortars in less stressed locations. Mortars exposed to weather differ from interior mortars. Foundation mortars have distinct characteristics from upper wall mortars. This demonstrates systematic understanding of how mortar properties related to application requirements, an understanding achieved entirely through empirical observation and practical experimentation. Every time a conservation specialist mixes traditional lime mortar to repair a historic building, they're participating in a technical tradition spanning centuries. The proportions they use, the mixing methods they employ, the curing procedures they follow, all descended from medieval practice. But the legacy goes further. Modern material science, as it investigates self-healing materials and sustainable alternatives to cement, repeatedly rediscovers principles embodied in medieval lime mortar. The cutting-edge research of 2026 often confirms the practical wisdom of builders who worked 8 centuries ago. Medieval mortar technology teaches us humility. These builders, without chemical theory or laboratory analysis, developed materials whose sophistication we're still working to fully understand. They show us that deep material knowledge can come from careful observation and systematic experimentation, not just from formal science. They also remind us that old doesn't mean obsolete. Sometimes, traditional materials embody wisdom that apparent progress has overlooked. The challenge is to combine the best of both the practical wisdom of traditional materials with the analytical understanding of modern science. As we face challenges of building sustainability, durability, and environmental impact in 2026, medieval lime mortar whispers across the centuries. There are other ways. Slower strength, longer life. Self-healing, not rigid. Working with nature, not against it. Not bad for a simple mixture of lime, sand, and water, mixed with centuries of observation, experimentation, and practical genius. Behind every magnificent medieval cathedral lies another often overlooked innovation, the sophisticated science of stone selection and preparation. Medieval builders developed deep knowledge of geology, stone properties, and how different stones performed in different applications. This knowledge, passed through generations and refined through experience, represents a form of materials science that modern engineers are only now fully appreciating. Medieval master masons were, in effect, practical geologists. They needed to identify suitable building stones, understand their properties, and match them to specific applications. This required detailed knowledge that went far beyond simple identification. A master mason could examine a stone and determine its load-bearing capacity, how it would weather over decades, its workability, ease of cutting and carving, its response to moisture and frost, its compatibility with different mortars, the best orientation for placement in a structure. This knowledge came from observation of existing buildings, quarrying experience, and systematic testing. Builders maintained mental, and sometimes written, catalogues of stone sources, noting which quarries produced stone best suited for foundations, which for decorative work, which for vaulting, which for exterior facing. One crucial understanding was the principle of the bed, the natural stratification layers in sedimentary stone. Stone laid with bedding planes horizontal, as they formed naturally, performed differently than stone laid with beds vertical or at other angles. Medieval builders knew that limestone, sandstone, and other stratified stones should generally be placed with beds horizontal. This prevented water infiltration along bedding planes and ensured the stone bore weight across its strongest axis rather than parallel to potential cleavage planes. Visit any well-preserved medieval building, and you can observe this principle in practice. The stonemasons carefully oriented each block to optimize its structural performance knowledge that came from observing failures when stones were improperly oriented. Medieval builders understood that freshly quarried stone often needed seasoning, a period of weathering and drying before use. Stone quarried in summer might be left exposed through a winter before being worked. This seasoning allowed quarry moisture to evaporate and revealed defects like internal cracks or weak layers that frost action might expose. Some quarries deliberately left stone exposed for years before sale, knowing that pre-weathered stone would perform better in construction. This practice demonstrated remarkable patience and long-term thinking, investing time and storage space to ensure superior material quality. Medieval builders matched stone types to specific applications with sophisticated understanding. Foundations: dense, hard stones resistant to ground moisture and capable of bearing enormous loads. Granite, hard limestone, or dense sandstone typically served foundation purposes. These stones could handle the perpetual dampness of soil contact without deteriorating. Load-bearing walls and columns: strong but workable stones that could be precisely cut and fitted. Medium-hard limestones or sandstones often served these purposes, providing good strength while allowing the precise cutting necessary for tight joints. Vaulting: relatively lightweight stones that could be cut to complex shapes. Too heavy stone would create excessive dead loads. Too soft stone might not have sufficient strength. The best vaulting stones balance these requirements. Exterior facing: weather-resistant stones that could withstand rain, frost, and atmospheric pollution. These needed fine texture for detailed carving, but had to resist erosion. The choice often involved trade-offs between workability and durability. Interior carving and decoration: softer, more workable stones that allowed fine detail. Since these weren't exposed to weather, durability was less critical than workability and appearance. Corbels and cantilevers: stones with good tensile strength, unusual in stone, which is typically weak in tension, or very dense, strong stones that could resist the unusual forces in projecting elements. This systematic matching of material properties to structural requirements represents sophisticated materials engineering, achieved without materials testing laboratories or formal engineering education. The location within a quarry affected stone quality. Medieval quarrymen knew that stone from different depths or areas of the same quarry could have different properties. Surface stone might be weathered. Stone from certain seams might be harder or softer. Stone from particular strata might have more consistent properties. This knowledge was economically valuable and often closely guarded. A quarry with reputation for particularly good building stone commanded premium prices. Master masons often developed relationships with specific quarries, knowing they could rely on consistent quality. Stone selection also involved practical considerations of transport. A superior stone source 5 days transport away might be less viable than an adequate source 1 day away. Water transport dramatically reduced costs, so quarries with river or canal access were highly valued. Medieval builders sometimes transporting stone remarkable distances for important projects. Caen stone from Normandy was shipped to England for prestigious buildings. Particular limestones were transporting across Europe for specific applications. But these cases involved careful calculation of whether superior material justified transport costs. The principles of medieval stone selection remain relevant in contemporary construction. Understanding which stones were used where and why guides appropriate repair and restoration. Replacing deteriorated stone with incompatible modern substitutes often fails because the replacement doesn't match original material properties. Modern stone suppliers and specifiers use similar principles when selecting stone for contemporary projects. The best practice is to match stone properties to application requirements, exactly what medieval builders did. Medieval attention to material properties and appropriate application meant stone wasn't wasted. Using the right stone in the right place, rather than one-size-fits-all approaches, represents sustainable practice we're rediscovering. While we now test stones in laboratories, measuring compressive strength, water absorption, freeze-thaw resistance, and other properties scientifically, we're essentially quantifying what medieval builders knew qualitatively. The principles remain the same. We've added precision and consistency. Medieval stone selection teaches several lessons relevant to modern construction. Material properties matter profoundly. Small differences in material characteristics can dramatically affect long-term performance. Taking time to understand and select appropriate materials pays dividends over building lifespans. Local knowledge has value. Understanding specific material sources, their variations, and their properties requires experience that can't be fully codified in specifications or databases. Patience in material preparation, seasoning stone, aging mortar, can improve quality more than rushing to build with fresh materials. One size doesn't fit all. Using the same material for all applications, because it's convenient or economical in the short term, often creates long-term problems. The medieval understanding of stone, achieved through centuries of observation, experimentation, and transmitted expertise, represents material science at its most practical and effective. Modern science has added precision, but the fundamental insights remain medieval achievements. Picture this. It's 1250 CE, and you need to lift a 3-ton stone block 30 meters into the air to set it in place on a cathedral vault. You have no motors, no diesel engines, no electricity, no steel cables. What you do have is human muscle, wood, rope, and ingenious engineering. Welcome to the world of medieval lifting technology, where innovation born of necessity created machines that would influence crane design for centuries. Medieval construction faced a fundamental challenge: how to lift extraordinary weights to extraordinary heights using only human or animal power. The scale of this challenge is hard to overstate. A single vault keystone might weigh several tons. Wall stones, roof timbers, bells, and other building elements routinely weighed more than dozens of people could lift directly. Simple solutions like ramps and levers work for modest heights, but become impractical for tall structures. Ramps to reach cathedral vaults would have required enormous amounts of material and space. Block and tackle systems help multiply force, but still require substantial initial lifting capacity. Medieval builders needed something better: machines that could efficiently translate human power into vertical lifting force. The most iconic medieval lifting device was the treadwheel crane. Essentially, a large wooden wheel that workers walked inside, like a hamster wheel, to generate rotational power that wound ropes and lifted loads. These weren't small devices. Surviving examples and historical evidence suggest wheels 4-5 meters in diameter were common, with some reaching 6 meters or more. One or two workers inside the wheel would walk, causing it to rotate. This rotation turned an axle connected to a winding drum, which pulled rope and lifted the load. The mechanical advantage was substantial: a treadwheel with a 4-meter diameter and a winding drum with a 0.2-meter diameter provided a 21 mechanical advantage. This meant two workers walking in the wheel could, theoretically, lift a load 40 times their combined weight. Practical efficiency losses reduced this, but the principle remained. Medieval treadwheels weren't crude devices. They incorporated sophisticated engineering features. Some cranes used wooden gears to further multiply force or change the direction of power transmission. These gears, carved from hardwood with carefully shaped teeth, demonstrated remarkable precision in medieval woodworking. Controlling descent was as important as achieving ascent. Cranes incorporated ratchets and pawls, catches that allowed rotation in one direction but prevented it in the other, to hold loads safely between lifting efforts. Some had friction brakes that could regulate descent speed. Many cranes could rotate, allowing them to lift loads from one location and deposit them in another. The rotation mechanism might be as simple as a vertical post pivot or as sophisticated as a ring of wooden wheels supporting the rotating superstructure. The projecting arms from which loads hung used clever engineering to handle the forces involved. These cantilevers needed to resist bending moments while remaining light enough not to overbalance the crane. Medieval carpenters developed truss-like structures with diagonal bracing that efficiently resisted these forces. Some cranes had multiple winding drums of different diameters, allowing operators to choose between faster lifting of lighter loads and slower lifting of heavier loads. Variable gearing, medieval style. Experienced builders incorporated redundancies. Backup pulls could catch a load if the primary system failed. Rope pathways were designed to prevent fouling. Structural members had safety factors built in through experience-based sizing rules. Treadwheel cranes were often permanent or semi-permanent installations built into the construction itself. They might be mounted on scaffolding towers, installed within the building as it rose, or even built into the final structure. Some cathedral towers contained spaces that once housed construction cranes. This strategic placement minimized horizontal movement of materials. The crane could lift materials vertically from ground level or a storage platform directly to where they were needed. Careful planning of crane locations was crucial to construction efficiency. Some cathedrals took centuries to build, and cranes might remain in place for generations, operated by different teams of workers as construction progressed. The famous unfinished cathedral at Beauvais had a treadwheel crane installed that remained in use for over a century. Treadwheels weren't the only lifting technology. Horizontal drums turned by radiating spokes provided mechanical advantage for lifting. Smaller and simpler than treadwheels, windlasses suited applications where lighter loads needed to be lifted frequently. For precisely positioning individual stones, medieval builders used Lewis devices metal pieces that inserted into dovetail-shaped holes cut in stone tops. These provided secure, damage-free lifting points for precisely lowering stones into position. Block and tackle arrangements used multiple pulleys to multiply force. Medieval builders understood the mechanical principles involved and used complex pulley systems for various applications. Some cranes used counterweights to balance loads, reducing the force human operators needed to provide. A heavy counterweight on one side of a lever could offset much of a load's weight, with human power needed only to overcome friction and provide the net lifting force. For some applications, horses or oxen provided power, walking in circles to turn a capstan vertical rotating drum that wound ropes. This provided consistent power for heavy lifting, but lacked the fine control of human-operated systems. Medieval lifting technology exemplifies innovation born from constraint. Without powerful motors, builders had to maximize efficiency in every aspect, optimizing rope paths to minimize friction, using the hardest available woods for bearing surfaces, carefully lubricating moving parts with animal fats, sizing structural members to be strong enough, but not wastefully heavy, training operators to work smoothly and rhythmically for maximum efficiency. These optimizations, developed through experience and systematic observation, represent practical engineering at its finest. You might think medieval cranes are purely historical curiosities, but their influence extends into modern engineering. The fundamental principles of using wheels, levers, and gears to multiply force remain central to modern machinery. Every crane, hoist, and elevator applies these principles, refined but not fundamentally changed since medieval times. In contexts where electricity is unavailable or undesirable, human-powered lifting devices descended from medieval technology remain useful. Hand-operated cranes for boats, wells, and remote construction still use treadwheel-inspired mechanisms. When divers need to manually position heavy objects underwater, they use mechanical advantage devices descended directly from medieval lifting technology. Because human muscle power, amplified by clever engineering, remains viable in contexts where powered machinery is impractical. As construction seeks to reduce energy consumption, interest is growing in human-powered construction aids for appropriate applications. Medieval lifting technology offers proven designs for efficient human-powered machinery. Some contemporary architects and engineers deliberately reference medieval cranes in their designs, celebrating the honest expression of structural forces and the beauty of purposeful engineering. Operating a treadwheel crane was skilled work. Operators needed to coordinate their movements for smooth, steady power delivery, judge loads, and adjust their efforts accordingly, respond quickly to signals from workers positioning loads above, maintain awareness of the crane's limits, and the load's behavior work safely despite being dozens of meters above ground. This required training, experience, and teamwork. The relationship between crane operators and the masons placing stones had to be seamless visual signals, traditional calls, and practiced coordination enabled precise placement of multi-ton loads. Medieval lifting technology demonstrates several timeless principles. First, mechanical advantage allows small forces applied over large distances to accomplish work requiring large forces over small distances. Medieval builders exploited this principle to its fullest using available materials and power sources. Second, careful engineering of force paths, ensuring forces flow through structural elements in compression rather than tension, minimizing bending moments, eliminating unnecessary complexity, produces efficient mechanisms. Third, safety through redundancy and failsafe design isn't a modern invention. Medieval builders incorporated backup systems, safety catches, and failure modes that prevented catastrophic accidents. Fourth, operational skill matters as much as equipment design. The best designed crane works poorly with unskilled operators. A simpler crane with experienced crew can outperform a complex machine with novices. Finally, constraints can drive innovation. Lacking motor power, medieval builders optimized human-powered systems to extraordinary efficiency. Modern engineers, facing different constraints, environmental, economic, energetic, can learn from this example of innovation within limits. The treadwheel crane and related medieval lifting technology represent human ingenuity at its finest, taking limited resources and available power sources, and through clever engineering, accomplishing seemingly impossible feats. When we see modern construction cranes lifting steel beams to build skyscrapers, we are watching the continuation of a tradition that began with medieval workers, walking inside wooden wheels to lift stone blocks to cathedral vaults. The scale has changed, the power source has changed, but the fundamental challenge, elevating mass against gravity, and the basic principles for addressing it remain rooted in medieval innovation. Those wooden wheels, turned by human footsteps, lifted entire cathedrals stone by stone. They remind us that given sufficient ingenuity, humans can accomplish extraordinary things with remarkably simple means. It's a lesson worth remembering in our technologically sophisticated age. While cranes lifted materials vertically, scaffolding provided the platforms where medieval builders actually worked. The development of sophisticated scaffolding systems was crucial to medieval construction achievements, yet it's often overlooked. These temporary structures sometimes rivaled the buildings themselves in engineering complexity, and the organizational systems for managing construction sites represented early forms of project management that influenced practices for centuries. Scaffolding might be temporary, but it had to be reliable. Medieval scaffolding supported workers, materials, tools, and the structures being built. A scaffolding collapse could kill dozens and destroy months or years of work. This meant scaffolding design was taken as seriously as the permanent buildings themselves. Medieval builders used several scaffolding approaches. Buildings were constructed with rows of square holes, put-log holes, left in walls at regular intervals. Horizontal timbers, put-logs, inserted into these holes cantilevered out from the wall, supporting planks that created working platforms. This system was elegant because the building itself partially supported the scaffolding. Many medieval buildings retain these holes, visible evidence of construction methods. For buildings where hole-put scaffolding was impractical, independent scaffold towers were built from ground level using timber frames. These required more material and more complex structural design, but offered flexibility in positioning and didn't leave holes in finished walls. Many projects used combinations, hole-put scaffolding where possible for economy, supplemented by independent towers where necessary. This optimized material use and structural efficiency. To move materials horizontally at height, medieval builders constructed bridges spanning between scaffold towers or connecting scaffolding to material hoists. These temporary bridges had to support heavy loads while maintaining stability. Scaffolding timber, typically straight-grained softwood or lighter hardwood, needed strength without excessive weight. Medieval carpenters developed techniques for joining scaffold components. Ropes made from plant fibers like hemp lashed timber into sections. Skilled workers could create strong, stable connections with rope alone. The lashing techniques, with specific patterns for different joints, were passed down through apprenticeship. Timbers were sometimes notched to interlock, with diagonal braces providing triangulation that stabilized rectangular frames against lateral forces. Wooden wedges driven into joints could tighten connections and adjust levels. Removable keys allowed disassembly and reuse of components. Scaffolding timber was valuable and was reused extensively. Well-maintained scaffold components might serve multiple projects over years. This economic reality drove durable construction and standardization of component sizes. While medieval safety standards weren't what modern regulations require, builders understood that accidents were costly. Several practices improved scaffolding safety. Working platforms sometimes had protective coverings above them to shield workers from dropped objects or falling debris from work on higher levels. Evidence suggests that railings or barriers at platform edges were sometimes used, particularly on heavily trafficked work platforms. Master masons or their assistants inspected scaffolding regularly, identifying worn ropes, cracked timbers, or structural problems before they caused accidents. Understanding that scaffolding had limits, builders controlled how much material was stored on platforms and how many workers occupied a given area simultaneously. Erecting and maintaining scaffolding was skilled work, often performed by specialized workers who understood structural principles and safety requirements. Beyond scaffolding itself, medieval construction sites represented early examples of complex project management. Building a cathedral involved stone, timber, mortar, metals, and other materials needed organized storage close to where they'd be used, but not obstructing work. Sites developed systematic layouts that optimized material flow. On-site workshops, lodges, provided covered space for stone cutting, carpentry, metalworking, and other crafts. These workshops needed organization, tool storage, workbench arrangement, material flow from raw to finished pieces. Large projects often included housing for workers, particularly specialists brought from distant locations. These temporary buildings needed their own infrastructure. Kitchens, stables, storage buildings, and administrative structures formed small temporary towns around major construction sites. Moving materials, bringing supplies, removing waste, accommodating visitors, and allowing ongoing liturgical functions in churches under expansion required thoughtful site organization. Valuable materials, tools, and partially completed work needed protection from theft, vandalism, and weather damage. Sites had security systems, walls, gates, guards, locked storage. On construction sites where work occurred at ground level and 40 meters up simultaneously, communication was crucial. Medieval sites used flags, hand signals, and positioned observers allowed communication across distances and heights. Bells, horns, or calls coordinated shift changes, breaks, and emergency responses. Workers designated to carry messages between site areas, workshops, and administrative locations facilitated coordination. Master masons and craft leaders met regularly to coordinate work, resolve problems, and plan upcoming tasks. The master mason was effectively the project manager, structural engineer, and chief architect combined. His responsibilities included overall design and engineering decisions, coordinating different trades and work crews, managing budgets and materials procurement, maintaining quality control, resolving technical problems as they arose, communicating with clients, typically church officials. Training apprentices and journeymen, this role required extraordinary skills, technical expertise, leadership ability, administrative competence, and practical wisdom. The best master masons were highly compensated and competed for by major projects. Construction followed seasonal patterns. Maximum activity, best weather, longest days, optimal conditions for mortar curing. Completing work that needed to weather seal before winter, preparing materials for next season. Reduced activity, cold weather prevented mortar work, but stone cutting, carpentry, and planning could continue in workshops. This rhythm required planning, ensuring sufficient progress during favorable seasons, preparing for winter slowdowns, managing workforce sizes that varied seasonally. Medieval scaffolding and site organization influenced modern practices. While modern scaffolding uses metal tubes rather than timber, the structural principles, frames, bracing, platforms, load distribution, derive from medieval practice. Modern construction project management, with its emphasis on coordination, scheduling, resource allocation, and communication, has roots in medieval master mason practices. The recognition that temporary structures require serious engineering, not just expedient assembly, comes from centuries of scaffolding design experience. Modern scaffolding uses standardized components that can be assembled in various configurations, direct descendants of medieval reusable scaffold component systems. Medieval scaffolding and site organization might seem like mundane logistics compared to dramatic architectural innovations, but they were essential enablers. You can't build a 40-meter-high vault without reliable scaffolding to work from. You can't coordinate hundreds of workers and tons of materials without systematic organization. These practical systems, developed through experience and necessity, represent the unglamorous but essential foundation of medieval construction achievements. They remind us that spectacular results require not just brilliant design, but also excellent execution, organization, and attention to practical details. The next time you see scaffolding on a modern construction site, recognize that you're looking at technology with medieval roots, updated in materials and standardization, but fundamentally continuing methods developed when builders needed to work at breathtaking heights using only timber, rope, and ingenuity. Here's one of the most remarkable aspects of medieval construction. Most of these magnificent buildings were constructed without detailed architectural drawings as we know them. No blueprints, no engineering calculations, no CAD models. Instead, medieval master masons used a sophisticated system of geometric design methods that encoded structural principles, proportional relationships, and construction procedures in geometric forms that could be laid out with simple tools. This wasn't primitive or imprecise. It was a highly developed design methodology that in many ways was perfectly suited to its context, and its principles continue to influence architectural design in ways both obvious and subtle. A medieval master mason's design toolkit was remarkably simple: a compass for drawing circles, and arcs a straight edge or square for drawing straight lines and right angles, a measuring rod or set of rods with specific lengths, marked sometimes geometric templates, thin pieces of material with curves or angles traced on them. Knowledge accumulated geometric principles and proportional systems passed through apprenticeship with these tools. Masons could design complete cathedrals, plan complex vault systems, and solve three-dimensional structural problems. The key was understanding how to use geometry to encode design information. One fundamental system was ad quadratum, design based on the square. The process might work like this. Start with a square representing the plan of a church nave. The width of the nave defines the square's side length. From this square, generate other dimensions geometrically. The diagonal of the square root 2 times the side length, might define column spacing or vault height. A square rotated 45 degrees inside the first square creates proportional relationships for aisle widths. Circles inscribed in or circumscribed around squares generate arcs for vaulting systems. Repeated geometric operations create a nested hierarchy of proportional relationships. The beauty of this system is that every dimension is proportionally related to every other dimension through geometric relationships. Change the fundamental module, the original square's size, and all other dimensions scale proportionally while maintaining their geometric relationships. This provides both flexibility, scale the design for different sites, and coherence. All parts relate harmoniously because they share geometric origins. Another system, ad triangulum, used equilateral triangles as the generative geometry. Triangular-based systems often produced steeper, more vertical proportions, perfect for Gothic's heavenward aspiration. A pointed Gothic arch can be generated from two circles whose centers lie at the base points and whose radii equal the span pure triangular geometry. Vault ribs, buttress angles, and tower proportions could all be derived from triangular relationships. Some buildings combined square and triangular systems, using each where its proportions were most appropriate. The transition between systems required understanding how they related geometrically, where a square root 2 progression from squares met a square root 3 progression from triangles. For example, the golden ratio, phi, approximately 1.618, appears in some medieval designs, though scholarly debate continues about how consciously and consistently it was applied. Whether intentionally pursued or emerging from other geometric operations, golden ratio proportions appear in dimensions of some medieval buildings. Other proportional systems included simple integer ratios, 1, 2, 2, 3, 3, 4, etc. Musical proportions, the same ratios that define musical harmonies. Nested geometric forms, squares within squares, circles within circles. Combinations of geometric and arithmetic progressions. The real sophistication came in applying these systems three-dimensionally. A plan drawn on the ground encoded not just horizontal dimensions, but vertical ones as well. The geometry that defined column positions also defined vault heights, the proportions of nave width related to clerestory height. Medieval builders developed methods for projecting three-dimensional forms from two-dimensional geometric plans. They understood that a square plan with specific circle intersections would produce a particular vault form when projected upward. They could read three-dimensional structural systems from two-dimensional geometric drawings. This required highly developed spatial reasoning, the ability to visualize complex three-dimensional forms from geometric information. It's a skill modern architects develop through extensive training with drawings, models, and computer visualizations. But medieval masons developed it through practical geometry and hands-on construction experience. Major projects often had tracing floors, large, flat, plastered surfaces where full-scale geometric layouts could be drawn. Master masons would lay out complex components full scale, allowing craftsmen to create templates directly from these drawings. Tracing floors served multiple purposes. Developing designs at full scale revealed practical issues not apparent at smaller scales. Templates, taken from full-scale drawings, ensured accurate production of components. Different crafts could coordinate their work using the same geometric references. Complex geometric operations were easier to perform at large scale, where precision was better. Some tracing floors had geometric constructions incised into the plaster reference lines and key relationships that could be used repeatedly as templates for systematic production of components. In an era with limited literacy, many craftsmen couldn't read text but understood geometry. Geometric systems were practical communication tools. A geometric layout conveyed design intent across language barriers and literacy levels. A stonemason who couldn't read written instructions could understand a geometric template perfectly. This geometric lingua franca facilitated knowledge transfer across Europe. A mason trained in France could work in Germany or England because they shared geometric design languages. The universality of geometric systems helped spread innovations and enabled the remarkable consistency of Gothic architecture across vast distances. Here's something remarkable that modern analysis has revealed. The proportional systems medieval builders used for aesthetic reasons often produced structurally sound results. The golden ratio proportions that created visual harmony also distributed loads efficiently. Triangular geometries that gave Gothic its vertical emphasis also generated favorable load paths. This wasn't coincidental. Medieval builders empirically discovered that certain proportions worked structurally and encoded them in geometric systems. The geometry that produced beauty also produced stability. Form and function weren't separate considerations. They emerged together from geometric relationships refined over generations. Modern structural analysis sometimes reveals that Gothic proportions are remarkably close to optimal from engineering perspectives. The geometric systems, developed through practical experience, embedded structural wisdom. The term sacred geometry sometimes appears in discussions of medieval architecture, suggesting mystical or esoteric meanings encoded in geometric relationships. The reality is more nuanced. Medieval builders and their patrons certainly understood symbolic meanings in geometric forms. Circles represented divine perfection, and eternity squares represented earthly creation and stability. Triangles symbolized the Trinity. Specific numbers had theological significance, but these symbolic associations coexisted with practical structural functions. A triangular proportion might be chosen both because it symbolized the Trinity and because it generated structurally efficient angles. The sacred and the practical weren't opposed, they reinforced each other. The sacred, in sacred geometry, might better be understood as recognizing that mathematics and geometry reveal divine order. Using geometry to design churches was participating in divine creativity. This theological understanding enhanced rather than replaced practical engineering. Master masons use geometry to solve practical construction problems. Problem: how to lay out a building foundation accurately. Solution: geometric construction from reference lines using squares and diagonals to ensure right angles and proper proportions. Problem: how to ensure columns are evenly spaced. Solution: divide the nave length geometrically using compass and straightedge. No measuring required beyond the basic module. Problem: how to determine vault height that will be structurally sound. Solution: use geometric relationships known to produce stable structures, derive height from plan dimensions through established geometric operations. Problem: how to coordinate multiple craftsmen working on related components. Solution: provide geometric templates generated from the same base geometry, ensuring components fit together despite being produced separately. This problem-solving approach was pragmatic and effective. It wasn't abstract mathematics. It was applied geometry serving practical construction needs. Medieval geometric design methods might seem obsolete in an age of computer-aided design, but they remain relevant. Modern parametric design software uses relational systems where changing one parameter automatically updates related elements, conceptually similar to medieval proportional systems where all dimensions related geometrically. Some contemporary architects use geometric rules to generate designs, computationally digital versions of medieval geometric design systems. Stonemasons, timber framers, and other traditional craftspeople still use geometric layout methods descended from medieval practice. These methods remain practical for certain applications. Teaching geometric design methods helps architects develop spatial reasoning and proportional thinking, skills valuable regardless of what design tools they ultimately use. Geometric proportional systems tend toward material efficiency and structural elegance qualities aligned with sustainable design goals. Some contemporary sustainable architecture deliberately returns to proportional design systems. In workshops restoring historical buildings, geometric design methods are kept alive. Craftspeople trained in these methods understand medieval buildings intimately because they think about design the way original builders did. This living tradition demonstrates that geometric design isn't obsolete. It's a viable alternative or complement to purely numerical/computational methods. For certain problems, especially in complex three-dimensional geometries, geometric reasoning can be more intuitive and direct than numerical calculations. Medieval geometric design teaches several valuable lessons. First, sophisticated design doesn't require sophisticated tools. With deep understanding of principles, simple tools can produce complex, excellent results. Second, proportional systems create coherence. When all parts of a design relate through shared geometric or proportional logic, the result has inherent harmony. Third, design systems that encode accumulated knowledge allow less experienced practitioners to achieve good results by following established patterns while learning underlying principles. Fourth, geometric/visual thinking complements numerical/analytical thinking. The best designers combine both modes of thought. Finally, methods that work across literacy and language barriers have power. Universal systems facilitate collaboration and knowledge transfer. The geometric design methods medieval master masons developed represent one of humanity's great intellectual achievements, a complete design system that could generate structures of magnificent complexity using only compass, straight edge, and accumulated wisdom. These methods weren't primitive approximations waiting for modern precision. They were sophisticated systems perfectly suited to their context, encoding centuries of structural knowledge in geometric forms that could be communicated, applied, and refined across generations. When modern architects use proportional systems, apply geometric reasoning, or recognize that certain proportions feel right, they're touching traditions that extend back to medieval workshops where master masons used circles, squares, and triangles to design buildings that still inspire awe 8 centuries later. The compass and straight edge. Simple tools, profound results, and a reminder that true sophistication lies not in tool complexity, but in depth of understanding. Before a single stone could be laid, medieval builders faced a crucial challenge: how to accurately lay out a building on the ground, ensure it was properly oriented, establish level surfaces, and create reference points that would guide construction for decades to come. This required sophisticated surveying knowledge and planning techniques that represent another often overlooked medieval innovation. Medieval surveyors worked with relatively simple but carefully designed instruments. Inherited from Roman practice, this consisted of a vertical staff with a horizontal crosspiece from which plumb bobs hung. By sighting along the plumb bob lines, surveyors could establish right angles and straight lines. The groma allowed accurate layout of perpendicular building lines, essential for establishing building plans on the ground. Weighted cords hanging vertically defined true vertical, water-filled troughs or channels established true horizontal. These simple tools, used skillfully, provided remarkable accuracy. Standardized rods of precisely known lengths allowed distance measurements. Sets of rods might include different lengths for different purposes. The accuracy of these rods was crucial. They were carefully made and maintained. Large wooden or metal triangles with carefully verified right angles allowed quick establishment of perpendicular lines and verification of layouts. Simple sighting devices, essentially tubes or frames that allowed looking along defined lines, helped establish long sight lines across sites. For determining cardinal directions, north, south, east, west, which was important for church orientation, surveyors sometimes used astronomical observations and instruments like astrolabes that could determine latitude and cardinal directions from star positions. Laying out a major building involved multiple steps. The site needed evaluation: soil conditions, drainage, topography, accessibility. Poor site selection could doom even well-engineered buildings. Medieval builders developed practical knowledge of soil testing, digging test pits, observing drainage patterns, examining vegetation as indicators of soil conditions. Churches were traditionally oriented east-west, with the altar at the east end. Precise orientation required astronomical observation, typically observing sunrise on specific days or using stellar observations. The accuracy of medieval church orientations, when analyzed, shows remarkable precision. Initial survey lines were established, typically along the main axes of the building. These lines might be marked with stakes, stones, or even trenches. They provided references for all subsequent work. The building plan was marked on the ground full scale. This involved using the reference lines and geometric methods to establish wall lines, column positions, and other features. Foundation trenches would be dug following these markings. Creating level foundations was crucial for structural stability. Medieval builders used water-filled channels. Water naturally seeks its own level to establish level lines. Posts or stakes cut to uniform height above these level lines provided level references across the site. Establishing plumb lines from which all vertical work could be referenced ensured walls rose truly vertical. These plumb lines might be permanent installations that remained through years of construction. The geometric design methods discussed earlier were applied directly to site layout. The compass and straightedge geometry, drawn at small scale or on tracing floors, was reproduced full scale on the ground. This required skill in geometric construction at large scale. Creating a perfect circle 30 meters in diameter using a rope and pivots, or ensuring a triangle spanning 50 meters was truly equilateral, demanded precision and technique. Medieval builders developed practical methods, using taut ropes or cords to maintain straight lines, employing multiple measurement techniques to verify accuracy, checking geometric relationships, for example, verifying that diagonals of a rectangle were equal, ensured it was truly rectangular. Not all sites were flat, level, and well drained. Medieval builders often worked with challenging conditions. Buildings on slopes required sophisticated understanding of how to establish level foundations on uneven ground, manage drainage, and accommodate level changes in building designs. Soft, unstable, or waterlogged soils required special foundation techniques, pile driving, using wooden piles driven to refusal, creating deeper foundations to reach stable ground, or using broad foundation walls that distributed loads over larger areas. Urban locations with existing buildings nearby required careful planning of access, material storage, and construction sequences. When expanding existing buildings, new work had to relate accurately to old. This required surveying existing structures and integrating them into new designs, challenging when old buildings might have settled, shifted, or been built to different geometric systems. How accurate was medieval surveying? Modern analysis provides answers. When researchers survey medieval buildings using contemporary instruments, they find overall dimensions typically accurate to within a few centimeters across spans of 50+ meters, right angles typically within a fraction of a degree, symmetry of building elements, like column spacing, remarkably consistent orientation for churches, often within a degree or two of true east. This accuracy is impressive given the tools available. It reflects not just careful work, but systematic checking and verification. Medieval builders understood that errors at foundation stage would propagate through the entire structure, so they invested time in getting layouts accurate. Beyond surveying, medieval builders engaged in sophisticated construction planning, determining what had to be built in what order, considering structural necessities, foundations before walls before vaults, access needs, how to get materials to upper levels, and seasonal limitations, what work could proceed in winter versus requiring warm weather, planning when materials would be needed, ordering from quarries and suppliers with appropriate lead times, arranging transport and storage. Large projects might involve contracts with quarries years in advance, specifying quantities, delivery schedules, and quality requirements, determining how many craftsmen of different trades would be needed at different construction phases, arranging for their accommodation and support, managing the transition from one phase to the next. While medieval accounting differed from modern practice, builders still needed to estimate costs, secure funding, and manage budgets. This required understanding material costs, labor rates, and how various design decisions affected expenses, identifying potential problems, difficult foundation conditions, material supply disruptions, weather delays, and developing contingency plans. Contemporary construction planning uses the same fundamental principles medieval builders applied. Accurate site surveying remains crucial for successful construction. Geometric layout methods, though now often assisted by lasers and GPS, follow similar logic to medieval techniques. Construction sequencing considers the same factors of structural necessity, access, and logistics. Material procurement requires similar advanced planning and coordination. The tools have changed dramatically: total stations, GPS, laser levels, computer modeling, but the fundamental challenges remain the same. Medieval surveyors and planners would recognize the problems modern construction planners solve, even if the methods would seem magical. Medieval surveying and planning teach valuable lessons. Accuracy matters from the start. Errors in initial layout cascade through projects, becoming more difficult and expensive to correct. Investing time in accurate surveying pays dividends. Simple tools in skilled hands can produce excellent results. Sophisticated equipment helps, but understanding principles and working carefully matters more than tool complexity. Practical knowledge complements theoretical understanding. Medieval builders developed practical tricks and techniques, ways to compensate for tool limitations, methods for verifying accuracy, strategies for dealing with common problems that represented applied intelligence. Long-term planning is essential for long-term projects. Medieval cathedrals took decades or centuries, requiring planning that looked far ahead, created flexibility for future needs, and enabled projects to survive transitions of leadership and workforce. Medieval surveying and construction planning might not be as visually dramatic as soaring vaults and flying buttresses, but they were equally essential to medieval construction achievements. You can't build cathedrals without knowing exactly where every stone goes, ensuring foundations are level and true, and planning how decades of work will unfold. These practical skills, developed through experience and refined across generations, enabled the dramatic architecture we celebrate. They remind us that magnificent results require not just brilliant design, but also careful execution, methodical planning, and attention to detail. The surveyor establishing foundation lines with a gromer and plumb line was as crucial to the cathedral as the master mason designing vaults with compass and straightedge. Together, they turned geometric visions into stone realities that still stand today. All the innovations we've discussed, the structural systems, materials science, construction methods, design techniques, had value only if they could be transmitted across generations. Medieval builders developed sophisticated systems for preserving and passing on knowledge, the guild system and apprenticeship training. These weren't just social organizations. They were knowledge management systems that successfully transmitted complex technical information across centuries. Medieval craft guilds emerged in the 11th and 12th centuries as craftsmen organized to protect their interests, control quality, manage training, and regulate their trades. For construction crafts, masons, carpenters, glaziers, metalworkers, and others, guilds became the primary institutions for knowledge preservation and transfer. A typical guild had hierarchical structure. Fully qualified craftsmen who had demonstrated competence completed required work, often including a masterpiece that showcased skill, and been accepted by existing guild masters. Masters could operate independent workshops, take on apprentices, and participate in guild governance. Qualified craftsmen who had completed apprenticeship but hadn't yet achieved master status. The term journeyman derives from French journée, day. They worked for daily wages rather than operating their own businesses. Journeymen could work for different masters, gaining experience and building reputations. Young people, typically starting in their early teens, bound by contract to masters for fixed terms, commonly 7 years. Apprentices learned the craft through hands-on work, observation, and instruction. They received food, housing, and training rather than wages. This structure created a systematic pathway for knowledge transfer. Apprentices learned from journeymen and masters. Journeymen refined their skills working on various projects. Masters maintained standards and passed on advanced knowledge. Medieval apprenticeship was sophisticated experiential education. First-year apprentices began with simple tasks, cleaning workshops, maintaining tools, preparing materials. These seemingly menial jobs built understanding of materials, tools, and workshop operation. An apprentice grinding stone, dust-off tools learned properties of different stones. One mixing mortar observed how proportions affected consistency and setting. As apprentices demonstrated capability, they tackled more complex tasks under supervision. A mason apprentice might progress from simple stone squaring to molding profiles to carving decorative elements. each level built on previous skills. Much learning happened by watching skilled craftsmen work. Apprentices observed techniques, absorbed methods, and tried to replicate what they saw. This observational learning was formalized. Apprentices were expected to watch attentively and ask questions. Apprentices spent thousands of hours practicing skills. This repetitive practice built muscle memory and intuitive understanding. A carpenter apprentice would cut countless joints by hand, developing the feel for when a chisel was sharp, how wood grain affected cutting, what sound indicated a good joint. As skills developed, apprentices received increased responsibility and independence. Late-term apprentices might work with minimal supervision, taking pride in producing quality work that contributed to projects. Alongside practical skills, apprentices learned geometric principles, proportional systems, structural concepts, and material properties. This might involve drawing exercises, studying exemplar buildings, or discussions with masters. Moving from apprentice to journeyman required demonstrating competence, often through creating test pieces that showed mastery of essential skills. Advancement to master status later required even more rigorous demonstration, including the famous masterpiece. Guilds were effective knowledge management systems. Guilds established standard practices, techniques, and quality benchmarks. This standardization meant knowledge could be transferred systematically rather than varying wildly among practitioners. Guild members inspected work, ensuring standards were maintained. This created accountability and provided learning opportunities. Masters examining apprentice work would explain deficiencies and demonstrate improvements. While guilds are sometimes portrayed as conservative and resistant to change, they also facilitated innovation sharing. Masters encountering novel techniques on one project might bring them back to their guilds and home regions. Guild meetings provided forums for discussing technical developments. Guilds did maintain some specialized knowledge, as trade secrets, particular techniques, material formulations, or design methods might be closely guarded. This gave guild members competitive advantages and protected their economic interests. However, the secrecy shouldn't be overstated. Basic knowledge was widely shared, and truly exceptional techniques often spread through journeymen who learned them and carried them to new regions. While much knowledge was oral and experiential, guilds sometimes maintained written records, regulations, standards, geometric constructions, or technical notes. These documents supplemented, but didn't replace hands-on training. One fascinating aspect of medieval masonry was the system of masons' marks, unique symbols individual masons carved on stones they cut. These marks served multiple functions. Marks identified who had cut particular stones, creating accountability for quality. If stones proved defective, the responsible mason could be identified. On large projects where masons were paid per stone produced, marks facilitated tracking individual production for payment purposes. Marks represented professional identity and pride in work. A mason's mark was personal, often inherited, with modifications, through families or passed from masters to favored apprentices. In some regions, masons' marks verified guild membership and qualification level. These marks, visible today on countless medieval buildings, provide tangible evidence of the individual craftsmen who built these structures. They're also evidence of systematic organization and quality management. On major construction sites, the Mason's Lodge served multiple purposes. A covered space for cutting stone, creating templates, crafting specialized pieces, and storing tools, where masons gathered during breaks, ate meals, and socialized. The lodge fostered fellowship and facilitated knowledge sharing through casual conversation and observation. Where apprentices worked under supervision, masters instructed, and skills were developed. Where the master mason managed projects, met with clients, and handled business, storing drawings, templates, geometric constructions, and accumulated documentation. Lodges were guilds' physical manifestations on construction sites. Their organization reflected guild values: hierarchy, collaboration, quality focus, and knowledge transmission. Medieval construction knowledge didn't stay local, it spread across Europe. Several mechanisms facilitated this. Young craftsmen traveled to work on different projects, learning regional variations and carrying knowledge back home. This journeyman years tradition meant builders experienced diverse approaches. Major projects recruited expert masters from distant regions, bringing their knowledge to new places. These masters often trained local craftsmen, who then applied learned techniques on subsequent projects. Guilds in different cities maintained connections, sometimes requiring travelers to demonstrate guild credentials, which created networks through which information flowed. When a new cathedral pioneered innovative techniques, builders from other regions could observe and study them. Major buildings served as three-dimensional textbooks of construction knowledge. The remarkable consistency of Gothic construction across Europe, from Spain to Scandinavia, from England to Eastern Europe, testifies to effective knowledge transfer. Buildings separated by thousands of kilometers use similar structural systems, proportions, and methods. The guild system wasn't perfect. Guilds could be exclusive, limiting access to trades and potentially stifling innovation from outsiders. Master-apprentice relationships sometimes favored family connections over pure merit. Guilds' strength and organization varied by region and trade, creating inconsistencies. Guilds sometimes used their monopolies to restrict competition or inflate prices. Conservative guilds occasionally resisted innovations that threatened established practices or members' positions. Despite limitations, guilds successfully transmitted complex knowledge across centuries, enabling the continuous development and refinement of construction techniques. Today's professional education and training systems are descendants of medieval guilds and apprenticeships. Modern architect and engineer licensing systems echo guild master qualifications, demonstrating knowledge and skill before practicing independently. Apprenticeships' DNA appears in modern internships, architectural residencies, and professional mentorship programs. Technical education institutions teaching construction trades continue apprenticeship traditions of progressive skill development and hands-on practice. Modern professional organizations, AIA for architects, various engineering societies, trade associations, serve some functions guilds once did, setting standards, facilitating knowledge exchange, maintaining professional identity. The recognition that experienced practitioners should guide newer professionals comes directly from the master-apprentice relationship. The guild system teaches valuable lessons. Knowledge transfer requires systematic approaches. You can't just give people books and expect competence. They need guided practice, progressive skill development, and experiential learning. Communities of practice preserve knowledge better than isolated individuals. Guilds created social structures that reinforced knowledge sharing and collective advancement. Quality control needs enforcement. The guild system of peer review and accountability maintained standards that benefited everyone. Long-term thinking matters. Apprenticeships lasted years, achieving mastery took decades. This patience produced deep expertise. Hands-on experience can't be replaced. No matter how good theoretical instruction becomes, actually doing the work remains essential for developing true competence. Medieval construction achievements were possible only because knowledge could be preserved and transmitted. The guild system and apprenticeship training, for all their imperfections, succeeded in transferring sophisticated technical knowledge across generations without written textbooks, formal schools, or standardized curricula. When we marvel at medieval cathedrals, we should also marvel at the systems that enabled their construction. The social and educational structures that turned raw talent into skilled expertise, preserved accumulated wisdom, and created communities of craftsmen who could accomplish together what no individual could achieve alone. These systems remind us that technical achievement isn't just about individual genius. It's about collective capacity, knowledge sharing, and institutional support for developing and maintaining expertise. The modern world, despite all its technological sophistication, still needs these lessons from medieval guilds. Now comes the crucial question. What do medieval cathedrals have to do with modern skyscrapers? On the surface, they seem completely different: stone versus steel, handcraft versus industrial production, faith versus commerce. But look deeper, and you'll find that modern high-rise construction is, in many ways, the continuation of structural innovations pioneered in medieval building. Both Gothic cathedral builders and modern skyscraper engineers face the same fundamental challenge: building tall structures that are stable, strong, and able to resist both gravity loads, the building's own weight, and lateral loads, primarily wind, though modern buildings must also consider earthquakes. The specific solutions differ because materials and tools differ, but the principles remain remarkably similar. Understanding these connections reveals that modern skyscrapers aren't disconnected from architectural history. They're the latest chapter in a story that includes medieval cathedrals as crucial earlier chapters. Medieval builders pioneered the concept of optimizing load paths, directing structural forces through specific elements rather than distributing them uniformly throughout massive structures. The pointed arch, ribbed vault, and flying buttress all exemplify this principle. Concentrate loads in efficient paths, place material only where structurally necessary. Modern skyscrapers use exactly the same principle, though with different specifics. Many skyscrapers use tube structural systems where the exterior walls form a hollow tube that resists both gravity and lateral loads. This is conceptually similar to the Gothic system of external buttresses and thin walls, placing structure at the perimeter to create interior freedom and structural efficiency. The Willis Tower, formerly Sears Tower in Chicago, uses a bundled tube system, multiple tubes working together. This is remarkably analogous to Gothic cathedral systems, where multiple buttressed bays work together as a unified structural system. Many tall buildings use a central core, housing elevators, stairs, and utilities, connected to exterior columns by outrigger trusses. These outriggers distribute lateral loads from the core to the perimeter, engaging the entire building in resisting wind forces. This is functionally similar to how flying buttresses distribute lateral vault thrust from upper walls to external piers, engaging external elements to resist internal forces. The geometry differs, but the structural logic is identical. Some contemporary towers use diagonal grid diagrid structural systems where crisscrossing diagonal members visible on the exterior carry all loads. The Hearst Tower in New York and 30 St. Mary Axe, the Gherkin, in London are prominent examples. These systems echo Gothic practice of making structure visible and using triangulated frameworks, while medieval builders used stone arches and buttresses, and modern engineers use steel diagonals. Both are triangulated systems that efficiently direct loads through compression members. Medieval builders developed sophisticated foundation techniques for dealing with challenging soil conditions. Large buildings concentrated enormous loads at column bases, exactly where flying buttresses met the ground. For instance, to handle these concentrated loads, medieval builders used stepped foundations that spread loads over larger areas, pile foundations, driven wooden piles. To reach stable soil, deep foundations that transferred loads below unstable surface layers. Modern foundations use the same principles with different materials. Spread footings perform the same function as medieval stepped foundations, pile foundations, now driven steel or cast concrete rather than wood. Still transfer loads to competent soil layers, caissons, and deep foundations, still reach through weak soils to stable bearing strata. The engineering calculations are more precise now, but the fundamental strategies come directly from medieval practice. Wind loads are critical for both tall cathedrals and tall skyscrapers. Medieval builders didn't have wind tunnel testing, but they empirically developed effective strategies for resisting lateral forces. The flying buttress system directly counteracts lateral thrust. Modern buildings use several analogous systems. Interior or exterior walls designed specifically to resist lateral forces function like vertical flying buttresses, transferring lateral loads to foundations. Rigid connections between beams and columns create frames that resist lateral forces through bending. These frames work somewhat like Gothic structural bays, where ribs, arches, and supports form rigid systems. Modern tall buildings sometimes incorporate mass dampers, heavy weights on springs or pendulums that counteract building motion. This is conceptually similar to how medieval builders used pinnacles atop buttress piers, adding mass to stabilize structures against lateral forces. Gothic structures incorporated redundancy, multiple load paths, backup systems, tolerance for partial failure. If one flying buttress underperformed, others could compensate. If mortar joints in one area deteriorated, the overall structure remained stable. Modern building codes mandate similar redundancy. Critical structures must be able to survive localized failures without catastrophic collapse. This redundancy principle, embedded in modern engineering practice, has medieval precedents. Medieval builders optimized material use because materials were expensive and difficult to transport. Every stone had to be quarried, shaped, transporting, and lifted into place by human labor. This drove innovation toward material efficiency, achieving required strength with minimum material. Modern sustainable design pursues similar goals for environmental reasons. Minimizing material use reduces environmental impact, energy consumption, and cost. Optimization algorithms that determine efficient structural forms often produce results resembling Gothic frameworks, material concentrated, where it's structurally necessary, minimal material elsewhere. Medieval builders adapted designs to specific site conditions, soil quality, topography, existing structures, available materials. No two Gothic cathedrals are identical because each responded to unique conditions. Modern skyscraper design follows the same principle. Each building responds to its specific site foundation conditions, local seismic or wind conditions, zoning requirements, adjacent structures. The best modern architecture, like the best medieval architecture, grows from specific conditions rather than imposing generic solutions. Gothic cathedrals were in their time analogous to modern skyscrapers, the tallest, most complex structures of their era, pushing technical limits, serving as civic symbols, requiring years to build and enormous investments. Both represent societies investing in monumental architecture that serves practical functions. Worship then, commercial/residential space now, but also symbolic ones, demonstrating capability, wealth, technical sophistication, and aspiration. The master mason designing a cathedral faced similar challenges to the structural engineer designing a skyscraper. How to achieve required height safely, how to resist lateral forces, how to manage construction logistics for a multi-year project, how to coordinate multiple trades and craftspeople, how to optimize structural efficiency, how to balance technical requirements with aesthetic ambitions. The scale has increased, the materials have changed, the mathematics has become more sophisticated, but the fundamental challenges and thinking processes remain remarkably similar. Some contemporary architects and engineers explicitly study medieval structures for inspiration. The Spanish architect/engineer designs structures that echo Gothic principles: visible structure, flowing forms, spatial drama. His buildings often feature external structural elements reminiscent of flying buttresses and ribbed vaults translated into modern materials. Foster's high-tech architecture often celebrates structure the way Gothic architecture did, making structural systems visible and beautiful. His 30 St Mary Axe building in London uses a diagrid system that creates Gothic-like visual rhythm and structural expression. Piano's light, transparent structures sometimes echo Gothic walls of glass. The modern wing of the Art Institute of Chicago, or the Shard in London, show influences of Gothic structural thinking: light, soaring, structurally expressive. Tracing the evolution of building heights shows direct lineage from Gothic to modern. Gothic cathedrals reached heights around 40-48 meters. Beauvais Cathedral's choir vault at 48 meters was among the tallest. As steel frame construction emerged, buildings passed medieval height records. The Eiffel Tower, 1889, 300 meters, demonstrated what was becoming possible. Steel-framed skyscrapers progressively grew taller. Woolworth Building, 1913, 241 meters. Empire State Building, 1931, 381 meters. Current tall buildings reach heights medieval builders couldn't imagine. Burj Khalifa, 828 meters. Numerous buildings exceeding 400-500 meters. But the structural principles didn't fundamentally change, they amplified. The lateral force resistance strategies in the Burj Khalifa, outriggers, buttressed core, setbacks that reduce wind loads, echo principles developed in Gothic cathedrals, scaled up and executed in modern materials. The connection between medieval cathedrals and modern skyscrapers teaches a crucial lesson. Architectural and engineering progress is evolutionary, not revolutionary. We don't discard everything previous generations learned and start fresh. Instead, we build on accumulated wisdom, applying eternal principles with new materials and methods. A structural engineer designing a skyscraper in 2026 is, whether they realize it or not, applying principles that medieval master masons pioneered. The mathematics is more sophisticated, the materials are stronger, the scale is larger, but the fundamental insight that intelligent structural systems can achieve heights that brute force cannot, comes from Gothic innovation. When you look at the Manhattan skyline or see the towers of Shanghai, you're looking at structures whose structural DNA includes genes from Gothic cathedrals. The pointed arch taught us about efficient load paths. The flying buttress showed us how external support can enable internal freedom. The ribbed vault demonstrated framework plus infill systems. The entire Gothic structural system proved that tall, light, dramatic spaces were possible through intelligent engineering. Modern skyscrapers are built from steel, concrete, and glass rather than stone and wood. They're analyzed with computers rather than geometric constructions. They're lifted by motorized cranes rather than treadwheels. But the fundamental challenges they address and the structural principles they apply have direct lineage to medieval innovations. The cathedral builders of the 12th and 13th centuries were, in a very real sense, the first skyscraper engineers. They pioneered principles that remain valid 8 centuries later. That's not ancient history, that's living legacy, actively shaping the buildings rising around us every day in 2026. As 21st century construction grapples with environmental challenges, climate change, resource depletion, energy consumption, waste generation, looking backward to medieval building practices offers surprising insights. Medieval builders, working within severe resource constraints, developed approaches that are remarkably aligned with modern sustainability goals. The most fundamental sustainability lesson from medieval construction is simply this: build things that last. The environmental impact of construction is amortized over the building's lifespan. A building that lasts 800 years, like many medieval structures have, has far lower annualized environmental impact than one that lasts 50 years. Medieval builders designed for permanence, using durable materials, stone, hardwood, lime mortar, creating structures that could be maintained and repaired rather than replaced, building with material systems that aged gracefully rather than deteriorating rapidly, designing for adaptability, so buildings could serve changing needs without reconstruction. Modern construction, with its emphasis on upfront cost minimization and typical design lifespans of 50-100 years, could learn from this long-term thinking. Some contemporary sustainable design advocates argue for a return to building for permanence, accepting higher initial costs in exchange for much longer service lives. Medieval construction relied primarily on local materials because transport was expensive and difficult. Stone came from nearby quarries, timber from regional forests, aggregates from local sources. This minimized transportation's environmental and economic costs. While medieval builders would transport special materials long distances for prestigious projects, the baseline approach was local sourcing. This reduced transportation energy and emissions, supported local economies, ensured materials were climatically appropriate. Locally available materials evolved to suit local conditions. created distinctive regional building traditions reflecting local material availability. Modern sustainable construction increasingly emphasizes local sourcing for similar reasons. While globalized supply chains offer cost advantages, they come with environmental costs, transportation emissions, packaging waste, disconnect from local conditions and traditions. The medieval model of primarily local materials, supplemented by carefully chosen specialty imports for critical applications, offers a balanced approach between pure localism and global sourcing. Medieval builders drive for material efficiency, using the minimum material necessary to achieve structural requirements, anticipated modern sustainability concerns. Every innovation we've discussed, pointed arches, flying buttresses, ribbed vaults, was partly driven by material economy. This efficiency came from deep understanding of material properties, placing material only where structurally necessary, using geometric optimization to maximize strength-to-weight ratios, careful craftsmanship that minimized waste. Modern sustainable design pursues similar goals through computational optimization. But the principle is identical. Don't use more material than necessary. Material extraction, processing, and transport are energy-intensive and environmentally impactful. Minimizing material use is environmentally beneficial. Medieval buildings breathe. They allow water vapor transmission through walls and roofs. This might seem like a deficiency, but it's actually sophisticated environmental design. Breathable construction prevents moisture accumulation that causes decay, mold, and unhealthy indoor environments, avoids the need for mechanical ventilation systems, and their energy consumption, creates self-regulating humidity levels that enhance comfort and health, allows buildings to dry naturally after wetting events. Modern construction's emphasis on airtight vapor barrier systems has created problems. Moisture trapped in walls, dependence on mechanical ventilation, indoor air quality issues. Some contemporary sustainable design returns to breathable systems, applying medieval principles with modern understanding. Medieval buildings used passive strategies for heating, cooling, lighting, and ventilation. Thick stone walls stored heat during day, released it at night, moderating temperature swings. Careful building orientation maximized beneficial solar gain in winter while minimizing summer overheating. Window placement, tower openings, and building form created natural airflow that ventilated spaces without mechanical systems. Large windows, enabled by Gothic structural systems, provided abundant natural light, reducing need for artificial lighting. Deep window reveals, overhangs, and other features controlled solar penetration. These passive strategies consumed no operational energy. They worked through intelligent design rather than mechanical systems. Modern sustainable design increasingly returns to these principles, using passive strategies before resorting to mechanical systems. Many medieval buildings have served multiple functions over centuries. Churches become museums, castles become residences, monastic buildings become schools. This adaptability extends useful life and avoids the environmental impact of demolition and reconstruction. Medieval structures often facilitate adaptation because large, open interior spaces can be subdivided flexibly. Durable construction can accommodate modifications. Simple, robust building systems can integrate modern services. Cultural value motivates preservation rather than replacement. Modern sustainable design increasingly emphasizes adaptive reuse and designing for long-term flexibility. The medieval model of buildings that serve multiple generations with evolving needs offers precedent and inspiration. Medieval construction relied on local craftspeople with deep material knowledge and practical expertise. This created buildings well suited to local conditions, ongoing maintenance capacity, local craftspeople who understood the buildings, skills passed through generations, economic benefit to local communities. Modern constructions, industrialization, and reliance on standardized systems has eroded this local expertise, sometimes creating problems. Buildings poorly adapted to specific contexts, maintenance, requiring specialized expertise from distant locations, loss of traditional craft knowledge, economic benefit, flowing to distant manufacturers rather than local communities' sustainable construction. Advocates increasingly recognize the value of craft knowledge and local expertise, both for creating appropriate buildings and for supporting resilient local economies. Medieval society had a repair culture. Buildings, tools, and objects were maintained, fixed, and kept in service for generations. This reflected both economic necessity, replacement was expensive, and cultural values, crafted objects had worth beyond mere function. Modern consumer culture tends toward replacement. When things break or age, we replace rather than repair. This generates enormous waste and environmental impact. Medieval repair culture offers lessons designed for repairability, accessible, understandable, using repairable materials. Maintain skills for repair and maintenance, value durability and quality over initial cost savings, accept patina and aging as adding character rather than indicating failure. Medieval buildings used natural, minimally processed materials. Stone quarried and shaped, but not chemically processed. Wood seasoned and cut, but not treated with synthetic chemicals. Lime mortar, produced through simple calcination. Natural fibers, metals, and pigments. These materials have lower embodied energy required for production, than highly processed modern materials, are typically non-toxic and safe for workers and occupants, can often return to the environment benignly at end of life. Don't depend on fossil fuel feedstocks, while modern materials offer performance advantages. The medieval emphasis on natural materials reminds us that simpler material systems can be adequate for many applications. With environmental benefits, we shouldn't romanticize medieval construction. It had significant limitations and problems. Labor conditions were often harsh. Buildings could be uncomfortable, cold, drafty, dark. Construction was slow and expensive. Structural failures did occur. Indoor air quality problems existed. Smoke from heating, poor ventilation. The point isn't to replicate medieval approaches wholesale, but to learn principles applicable to modern contexts. We can combine medieval wisdom about durability, material efficiency, and passive environmental strategies with modern understanding of comfort, safety, and structural analysis. The most promising sustainable design approach combines medieval principles, durability, material efficiency, passive strategies, local sourcing, craft knowledge, modern capabilities, analytical understanding, advanced materials where appropriate, mechanical systems for comfort, precision engineering. This integrated approach might produce buildings that last centuries. Medieval longevity, provide excellent comfort and functionality. Modern standards, minimize environmental impact. Medieval material efficiency plus modern analysis, support local economies and cultures. Medieval craft traditions plus modern technology, age gracefully and can be maintained sustainably. Medieval material systems plus modern preservation science. Some contemporary projects explicitly learn from medieval practice. Projects using lime mortar, locally sourced stone, traditional timber framing, medieval methods for new buildings. Ultra-efficient buildings using passive strategies medieval builders pioneered, combined with modern insulation and airtightness. Designing buildings for disassembly and material reuse echoes medieval practice of salvaging and reusing building materials. Research into self-healing materials learns from lime mortar. Studies of natural material composites learn from traditional building methods. Medieval construction, born from resource constraints and pre-industrial technology, developed approaches remarkably aligned with 21st century sustainability imperatives. This isn't coincidence. Both medieval builders and contemporary sustainable designers face the challenge of accomplishing maximum results with minimum environmental impact. The specific solutions differ. We have better materials, more sophisticated analysis, different constraints, but the principles remain valid. Build for permanence, optimize material use, employ passive environmental strategies, source locally where practical, maintain craft knowledge, and repair culture, use natural, minimally processed materials, where appropriate as construction in 2026, confronts climate change and resource constraints. Medieval building wisdom offers not nostalgic retreat, but practical inspiration, time-tested principles for building well with limited resources and lasting impact. The most sustainable building medieval builders understood is one that never needs to be replaced. 8 centuries later, their work proves the point. We've journeyed from pointed arches to modern skyscrapers, from lime mortar to self-healing concrete, from treadwheel cranes to contemporary construction equipment, from master masons' geometry to parametric design. The journey reveals something profound. The history of building technology isn't a series of disconnected breakthroughs, but an unbroken chain of accumulated wisdom, refined across centuries. Let's recap the astonishing connections we've uncovered. The pointed arch, flying buttress, and ribbed vault weren't just medieval architectural elements. They pioneered principles of load path optimization, material efficiency, and structural redundancy that remain fundamental to modern engineering. Today's skyscraper structural systems are direct descendants, applying the same principles with different materials. Medieval lime mortar, with its self-healing properties and centuries-long performance, teaches lessons modern materials science is only now fully appreciating. Research into self-healing concrete and sustainable building materials often rediscovers what medieval builders knew empirically. From treadwheel cranes to scaffolding systems, medieval builders developed sophisticated construction methods using human power and mechanical advantage. These innovations laid groundwork for modern construction equipment and project management. Master masons' geometric design systems, using simple tools to create complex, structurally sound, aesthetically harmonious buildings, anticipated modern parametric and generative design approaches. The principles remain valid even as tools have changed. The guild and apprenticeship system successfully transmitted complex technical knowledge across centuries without textbooks or formal schooling. This knowledge management success offers lessons for contemporary professional education. Medieval construction's emphasis on durability, material efficiency, local sourcing, and passive environmental strategies aligns perfectly with modern sustainability goals. Old wisdom addresses new challenges. Perhaps the most important revelation is that innovation doesn't discard the past, it builds on it. The greatest medieval innovations weren't entirely new inventions. They were creative recombinations and refinements of existing elements. The pointed arch existed before Gothic architecture. Gothic builders perfected its structural application. Roman concrete was sophisticated. Medieval lime mortar adapted and refined it for different contexts. Similarly, modern innovations build on medieval foundations. Computational structural optimization produces solutions remarkably similar to Gothic structural systems because both respond to the same physical laws and engineering objectives. Self-healing materials research rediscovers principles embodied in lime mortar. Sustainable design returns to passive strategies medieval builders pioneered. This continuity means that studying historical building technology isn't just antiquarian interest, it's practical education. Understanding how previous generations solved problems illuminates how we might solve similar challenges today. Medieval innovations emerged from constraints. Limited materials, no steel, no modern concrete. Limited power sources, human and animal muscle. Limited tools, no motors, no computers. Limited transportation, moving materials was difficult and expensive. Rather than preventing achievement, these constraints drove creativity. Medieval builders couldn't overpower problems with brute force or advanced materials. They had to be clever. They had to understand materials deeply, use geometry intelligently, optimize structural systems carefully. Modern construction, with seemingly unlimited power and material options, sometimes forgets the lessons of constraint-driven innovation. We can overpower problems, use excessive material, pour energy into mechanical systems, accept inefficiency because it's economically tolerable. But as we face new constraints, environmental limits, climate change, resource depletion, The medieval example of innovation within constraints becomes newly relevant. How do you accomplish maximum results with minimum resource consumption? Medieval builders answered that question brilliantly. Behind every innovation we've discussed were people, individual master masons, anonymous craftspeople, generations of apprentices who observed carefully, experimented systematically, and refined techniques painstakingly. These weren't scientists in laboratories or engineers with advanced degrees. They were practical builders who learned through experience and transmitted knowledge through demonstration and practice. Yet they achieved sophisticated understanding that modern science often validates rather than contradicts. This reminds us that deep knowledge can emerge from practical engagement and careful observation, not just from formal theoretical education. The best modern practitioners combine both theoretical understanding and practical wisdom. Medieval builders could teach us about the value of hands-on experience and empirical learning. Some valuable knowledge from medieval practice has been forgotten or nearly forgotten. Lime mortar techniques were largely abandoned in the 20th century, creating problems when modern cement was used inappropriately on historic buildings. Traditional stone conservation methods were replaced by techniques that sometimes caused more damage than they prevented. Craft skills for maintaining historic buildings declined as modern construction, industrialized understanding of passive environmental strategies faded as mechanical systems became cheap and ubiquitous. When knowledge is lost, we sometimes have to painfully rediscover it. The revival of lime mortar use in conservation, the return to passive design strategies, and the renewed interest in traditional craft skills all represent rediscovery of medieval wisdom. This suggests we should be careful about dismissing traditional knowledge as obsolete. Sometimes old wisdom addresses challenges better than modern approaches, and sometimes it offers insights that can enhance modern methods. As construction in 2026 and beyond faces significant challenges, medieval principles offer guidance. Medieval material efficiency, durability emphasis, and passive environmental strategies provide models for low-impact building. As materials become more expensive and environmental impacts more concerning, medieval optimization and local sourcing become increasingly relevant. In a world of disposable construction, medieval emphasis on quality, durability, and craft offers alternative values. As skilled trades face workforce challenges, medieval apprenticeship models suggest effective training approaches. Medieval buildings' connection to local materials, local skills, and local needs offers alternatives to globalized, placeless construction. This exploration of medieval building innovation invites several responses. Study historical structures not as museum pieces, but as case studies in creative problem solving. The lessons remain relevant. Consider how medieval principles might inform contemporary practice. Take pride in participating in traditions extending back centuries. The skills you practice, the problems you solve, connect you to generations of craftspeople who faced similar challenges. Recognize that your education builds on centuries of accumulated wisdom. Understanding historical precedents enriches your ability to innovate for the future. When you encounter old buildings, see them not as quaint relics, but as sophisticated engineering achievements that have already demonstrated value by surviving centuries. They have lessons to teach if we're willing to observe and learn. The myth this script aimed to bust is the notion that medieval building was primitive, that modern construction represents a complete break from the past, that history has nothing to teach contemporary practice. The truth is far more interesting. Medieval builders pioneered innovations that remain fundamental to modern construction. They solved problems with remarkable creativity and developed knowledge that we're still learning from. The chain from medieval workshop to modern construction site is unbroken. When structural engineers design the skyscrapers of 2026, they're applying principles medieval master masons pioneered. When materials scientists develop advanced concretes, they're often rediscovering what medieval mortar formulations embodied. When sustainable designers pursue durability and efficiency, They're returning to values medieval builders exemplified. The secret origin story of modern construction runs through Gothic cathedrals, master masons' geometry, medieval cranes, and lime mortar workshops. These aren't ancient history, they're living heritage, actively shaping how we build today. Next time you see a pointed arch, a soaring vault, or a centuries-old stone building still standing strong, recognize that you're looking at the roots of modern building technology. Those medieval innovations forged in workshop practice, refined through generations, built to last forever, are still shaping the skylines of 2026. The medieval builders who created them will be proud to know their work continues, adapted and evolved, but fundamentally still present in every building we construct. That's not just history, that's legacy, living and vital, and continuing into the future we're building right now. Imagine the towering skyscrapers and sleek bridges of February 2026. Now you know their secrets were uncovered not just in modern labs, but in dusty medieval workshops. You've had your mind blown as we've unveiled the forgotten medieval innovations, from revolutionary arches to hidden material science, that are still secretly shaping the skylines you see every single day. You'll never view today's architecture the same way again. The next time you walk past a modern glass tower, remember the pointed arches that taught us about load paths. When you admire a building's structural elegance, think of the flying buttresses that showed us external support could enable internal freedom. When you hear about self-healing concrete, recall the lime mortar that pioneered the concept 8 centuries ago. Medieval master builders weren't primitive. They were pioneers, innovators, and problem solvers whose insights remain valid in an age of computers and steel. Their genius wasn't in having advanced tools. It was in understanding fundamental principles so deeply that their solutions remain relevant regardless of materials or technology. That's the real story of forgotten medieval innovations. They were never really forgotten. They became so fundamental to how we build that we stopped noticing them. They're the invisible foundation on which all modern construction stands. And that, ultimately, is the highest compliment any innovation can receive. To become so successful, so essential, so perfectly integrated into practice that it becomes invisible, not because it was forgotten, but because it became fundamental. Thank you for joining this journey through the secret history of building technology. May you never look at old buildings, or new ones, quite the same way again.